Thank you, Niccolo. So good morning and hello to everybody here. Welcome to the webinar organized jointly by TREX, the Center of Excellence TREX, and the CECAM. So in this webinar, we'd like to propose 5 speakers covering different domains across the broad theme of condensed matter. So we're gonna cover and see topics about layered materials, surface physics, high pressure physics, magnetism, and energy excitations. So of course the focus will be the use of quantum Monte Carlo techniques. That will be sort of the main star here. And to start the discussions and the webinar, I'd like to give the floor to first Sara Bonella, who's the Deputy Director of CECAM. Please, Sara.
Thank you very much, Michele. And thank you, TREX, for offering the opportunity for this collaboration between you and CECAM. Now, CECAM is the French acronym for the European Center for Atomistic and Molecular Simulations. We are, I would say, the oldest institution devoted to sharing knowledge and fostering progress in computational sciences. CECAM was created in 1969, originally as a single institute in Paris, and we are nowadays a network of 19 nodes scattered across Europe, which for CECAM includes Israel, Switzerland, and even the UK. And we recently opened our first node in the United States, thanks to our collaboration with the University of Chicago. Now, I think that the best way to get to know us, if you don't already, is to explore our website. So here it is. I just wanted to show it to you. Here you can find information about upcoming events. Here is the current webinar, but also the full program of activities that we organize at CECAM are our core activities targeted at introducing a new generation to the latest advances in computational science, but also enabling discussion on open questions between leading experts in our domain. CECAM has also been engaged in other activities, and if you dare to go to the other activities part of the website, you will see a few of them. And these include European funded projects, not just funded by Europe, but in particular, now let's discuss about the European funded projects. And among these projects, there are those that are, focused on not only, the development of new methods and new algorithms in simulation and modeling, which is probably the original focus of the CECAM nature, but also looking at the tools that we use in order to effectively deploy these algorithms and these methods in strategy. There has been a growing engagement of CECAM with the Centers of Excellence for Computing Applications funded by the European Commission. We have been the coordinating institution of one of them. It was called ECAM, and it ended its activities in 2020. We are actively involved with other COEs like MAX and in particular the Multiscale Center of Excellence. And we enjoy good collaborations and good relationships, hopefully, with most of them. Including in particular today, TREX. And so it gives me real pleasure of webinars. We're very, very grateful to TREX for inviting us to be part of this adventure, and also for organizing and taking the burden of most of the organization for today. Very much looking forward to learning something about the most recent applications of Quantum Monte Carlo in the HPC domain. Thank you.
Thank you, Sara. So as you mentioned, we'd like to show somehow the applications of Quantum Monte Carlo and how Quantum Monte Carlo can give some answers to some important problems. And this has been developed within the TREX consortium also, not only, but so part of this seminar is also to show some results obtained within TREX. And that's why I'm pleased to give the floor to Claudia Filippi, who's the coordinator of TREX. Please, Claudia.
Thank you, Michele. Well, welcome everybody. Thank you also, Sarah, for joining in this webinar, for helping us in these webinars. I will say a few words about a Center of Excellence. Already Sarah mentioned it. So a Center of Excellence is a project, a large project. For us, it was supported by the European Commission under Framework 2020. And so there are various Center of Excellence focused on different applications, and the idea is actually to bring this code and also the related community to be able to effectively exploit the new machines, large machines, which are being built in Europe. Okay, for TREX, which stands for Targeting Real Chemical Accuracy at the EXascale, the focus is on Quantum Monte Carlo methods. And as you're going to hear later, these are very accurate methods that can be used for condensed system, also for molecular system. They're massively parallelizable. So you can think about Monte Carlo, even though it's quantum, it has a lot of trajectories. You can relatively easily parallelize. Is very CPU intensive, so you are very compute hungry methods. And the point is we're also still under development. That's the reason why to have TREX, you know, so we want to run our codes, but we can also need to develop our codes in terms of algorithm and in terms of being able to exploit, you know, for instance, hybrid architectures. So indeed, the objective of our Center of Excellence was to make the codes ready for EXascale. So there are various codes which we improved, but also we developed two libraries which are taking care of the high-performance part of our applications, in particular the QNCKL library for indeed, you know, most kernels of Quantum Monte Carlo, as well as TREX.io, which is a library which is handling exchange of wave function information between different codes inside and outside TREX. So these are the partners. So we are chemists, physicists, there are some machine learning experts. Of course, we have software and HPC experts, as well as technical and communication SMEs. And then we're also having representatives, which are also going to be here, of the user communities. So indeed, you know, so TREX, you know, has resulted in a platform of software, as I mentioned, the two libraries, as well as a bunch of codes, you know, which have been improved, refactored, and modularized to actually make use of the library. So these are real space Quantum Monte Carlo. We are having, you know, CHAMP, QNC equal to CAM, and TurboVB. Nessie, that's full CI Quantum Monte Carlo, and we're also having two deterministic, a bit, you know, high accuracy code, Quantum Package for sophisticated selective CI type of approaches, and GAN-Core, which is handling various many-body approaches to study interaction, you know, weak interaction in supermolecular systems. We are having machine learning tools integrated in our workflows, which are using AIDA for workflow management and high throughput computing. Now, what is important is a website. So we're having a website, which is the main website for TREX, as well as a GitHub a repository where you can find, you know, when you can reach all the software and all the codes. And finally, this is a picture of us a few years ago, I will say when we started in Versailles from our partner, and I will let you now the floor to the following speakers. So.
Okay, thanks, Claudia, for this introduction. So now we enter into the more scientific part of the webinar by listening to the first invited speaker, who's Ivan Stik, professor at the Slovak Academy of Science in Bratislava, and he will be talking about layered materials, and in particular about a Quantum Monte Carlo study of straintronics response of 2D materials, monolayer phosphorine and MOS2. So please, Ivan, you have 25 minutes, and then we'll leave 5 minutes for questions and discussions after your talk. Please.
Okay, yeah, thank you, Michele. I cannot share because somebody else is sharing. Ah, okay. Okay, so good morning, everybody. So let me start by thanking the organizers for inviting me to give this presentation in this webinar. So, as already said, I will be talking about QMC calculations on 2D materials. And I will specifically be discussing application of external strain onto two different 2D monolayer systems, namely phosphorine and molybdenum disulfide. These first two people are those who did most of these calculations, but we were also very happy to have two more people involved in our project, namely Luboš Mitaš, who is the so-called titan in QMC, and also Professor Fabian, who is very knowledgeable in the 2D systems. Okay, so I will have one slide introduction into 2D materials, and then I will go and jump right into the calculations and studies we have done. And in particular, I will be discussing two systems, phosphorine and MOS2. MOS2 is what I would call quintessential straintronic material. Many experiments exist, straintronic experiments exist for this system. And my main sort of outcome of these calculations will be phase diagram of the different excitations. So I will outline the boundaries where the different band gap types are realized, and I will be comparing these two systems. Okay, so 2D materials are perhaps the most studied, currently studied systems, and they can be prepared simply by Scotch tape exfoliation. The Nobel Prize was awarded for graphene some 13, 14 years ago. And the electronic properties span all the range from metals all the way to wide gap insulators, but perhaps the most important ones are the semiconducting systems. And the representatives I will be talking here will be transition metal dichalcogenides and phosphorine. These materials typically feature very high carrier mobility and very often direct band gap, as will also be evident from this presentation. The other property which I would like to highlight here is that these materials are extremely strainable. They typically can sustain strains well in excess of 10%. For example, in graphene, it's measured at about 25%, and in molybdenum disulfide, it's still about 11%. The strain can be actually used to tune the electronic properties of these materials, such as band gap, for example. Here is an example of phosphorine, which spans the band gap somewhere between graphene, which is a semi-metal, and wide gap insulator, semiconductors such as TMDs. So this is the gap where I can actually strain, when I can tune the properties by application of strain. I would like to remind you that by applying strain, you can change a number of properties. One such important property is carrier mobility. And I will not really go much into that because it's something which is difficult to calculate by QMC, but we should keep that in mind. Okay, so what accuracy we actually need and what can be achieved by current computational techniques. So let me use monolayer phosphorine as an example. Let me start by experimental results. So this is the value which is measured on freestanding sample. This is a very rare result because normally these materials are supported on some materials which heavily interfere with their electronic properties, but this was a suspended sample. So this is a very, very valuable reference point these are the DFT results, which typically underestimate the results, and these are the GW results, where you would expect that they are very close to the experiment, but yet there is a very huge spread of these results here, and this is our best QMC result, which is almost in within chemical accuracy with the experiment, because we do not have any vibronic effects included, etc., which would lower the value of the band gap. So from this slide, it is clear that we need methods which have much better accuracy than DFT and even GW. And if I apply strain, things may only get worse. So this is why we do these QMC calculations. So let me now talk about application of strain to phosphorine. So what we started with was pre-screening by DFT methods. So this is the band gap as a function of two strains. This is strain in the zigzag direction, and this is strain in the armchair direction, as shown here. And as you can see here, there is a large part here which is the direct gamma to gamma gap. This type of electronic structure. Then we have another part here which is still gamma to gamma transition. But as you can see here, there is an abrupt change in the electronic structure because the order of the bands has been switched due to the strain. And then there is also a part where these excitations are indirect, that is gamma to X, as shown here. So here we have an abrupt change, I call it gamma to gamma prime, where we have changed the order of the bands. And actually, by doing that, we change also the electronic and transport properties because the curvature of the bands is different there. Okay, so there is a plethora of other excitations here, but I will only be talking these boundaries here between gamma and gamma prime and gamma and X. So I will outline them by QMC. So let me now talk QMC calculations. So these are very early calculations here. So first you can see here I apply a tensile strain of 2.5% and a compressive strain of -1%. So you see that by doing that, I have changed the band gap by about half a volt, which is really a lot. Then there is another interesting property here. Here is from equilibrium, there is a change of 1%. Here is 2.5, and this it scales linearly with the band gap. This is very hard to understand, really. But the only way how this can be rationalized is that these parabolas of ground and excited states are essentially identical. They are only a little bit shifted. Of course, they are offset vertically, but they are a little bit shifted also laterally, and that explains this linear scaling of the band gap. So what we do in the calculations, we have a problem where we have 4 parameters, 4 variables. We have A and B lattice parameter, and we have 2 internal parameters, which I call X and Y. So we have for the problem, so we have quadrivariate function, which we fit by paraboloid functions. And we always minimize then with respect to X and Y. We need to be in equilibrium at each A and B. And all this is done by bracketing these minima by at least 25 QMC calculated points. And by doing that, then I can actually end up with a bivariate function by minimizing with respect to X and Y. And the excited state is only calculated at the equilibrium, so that's strictly a 2-dimensional function. Okay, so this is now what we do. I need to do finite size scaling. So this is the gamma to gamma. So I do a number of calculations at differently sized approximates. For gamma will always refold onto gamma, so I can take any cell. But if I, for example, do these other excitation gamma to X, not all cells will refold X onto gamma. For example, the smallest one will not. So these are the results of the finite size scaling. So you see the corrections are very sizable here. Sorry, are very sizable here. And so what I have here are these 7 points as shown here. This corresponds to minimum. And so I have these 7 curves here for 3 different excitations. And I would like to remind you that there is no twist averaging here, which makes these calculations really expensive, because I really need to take an electron from a particular K point and put it in a particular K point. So no twist averaging would help us here. So that's why what makes these calculations really numerically very, very expensive. Okay, let me start by equilibrium properties. The first, and I will be comparing with the 3D black phosphorus crystal. And so the first thing you see in the structure is that this B parameter in the armchair is much larger than in the crystal. So can we understand it? And I will show you that we can. The other thing we can see here is that these QMC calculations results are very similar to DFP, BE, DFT. So these are our parameters we calculate, and I would like to remind you they cannot be determined experimentally, because typically I have the substrate there which will modify these results, in this case in particular quite substantially. However, the results agree only for PBE, which is accidental. But if I use different functionals, such as for example Beast relief, I would be 4% off with respect to the QMC. And there are also these bilayer systems which sort of emulate the substrate, and you can actually see why these distances are changed, because these are QMC calculated charge densities, and you see that this bilayer in phosphorine is actually partially chemically interacting. And that also means that if you put this on a substrate, this single layer, monolayer, it will also likely interact with the substrate, which will change the electronic, which will change the atomic structure. And that doesn't happen, for example, in MOS2, where there is no interaction whatsoever, pure van der Waals. Okay, so let me now compare the band gap, which I have shown already on the first slide, and the agreement is really spot on with the experiment. So we have almost chemical accuracy here. Now, straintronic. So this is the gamma to gamma excitation, how it scales with applied strain, and you see it's almost a plane here. We have added 2 more points here to have better approximation by this paraboloid modeling. And okay, and this is what is very important factor is so-called gauge factor, which says what is the change of the band gap for a percentage of applied strain. So first of all, you see that these gauge factors are very similar with results from DFT modeling, and the result is that these potential energy surfaces are actually parallel. So there is no reason why they are offset vertically, but otherwise they are quite parallel. And the gauge factor is huge. It's roughly 100 milli-electron volt per percent, which is comparable to the MOS2, which is regarded the straintronic reference here. Okay, I have said how the gamma to so far studied how the gamma to gamma excitation is scaling with the strain. I would now like to outline the region where this gamma to gamma excitation is realized, and I can do that by studying the potential energy surfaces for different excitations, and from the intersections I can determine the boundaries. This is what is done here. This is gamma to gamma prime. This is gamma to gamma and gamma to X. And from that, I can construct this sort of phase diagram where you see this gamma to gamma region. Then there is gamma to gamma prime, gamma to X. These are the lines we have outlined, and these are the error bars we have on our calculation here. All the rest is actually DFT here. So what you can conclude from here, we have a very large gauge factor, and this region is truly huge where I can tune that. This is like 10% here, and also 10%, this is enormous. And for that reason, we call it a colossal response in phosphorine, and you can tune the band gap by 1 electron volt roughly, which is unheard of, I believe, by application of the strain. Here is the DFT result. So the region is much smaller, about factor 2 smaller. And even if you do other functionals, it won't really call it even quantitatively change very much. Okay, now we can calculate the deformation energy. So this is comparison of QMC with PBE that agrees pretty well, but the other functionals may not agree that well, such as, for example, this B3 which is partially due to the disagreement in the lattice, but also the curvature is much larger here. Okay, one thing I'd like to mention is the so-called Poisson's ratio, which we have calculated from our QMC results. And this is the strain, this is the relation between strain in A and strain either in B or the perpendicular strain in the Z direction. And normally materials, if you strain them, if you stretch them, they would shrink in the middle. This is what is called positive Poisson's ratio. Some materials, maybe mainly the man-made materials, have a different property that if you stretch them at the ends, they will expand in the middle, which is called negative Poisson's ratio. And this is what we see here. In plane, we see a positive Poisson's ratio, whereas here I stretch the system and the system actually swells in the perpendicular direction. And this is what is called auxetic material. So phosphorine is auxetic material. Okay, now very quickly, let me wrap up the results we have for MOS2. So we do precisely the same as we did for phosphorine, but we only apply diagonal strain, which means everything shrinks down in 2 dimensions, and basically we end up with an energy as a function of the lattice parameter, and the same for the excited state. There is one caveat though here, namely that we need to take spin orbit couplings into account here. They are not large, but they are non-negligible. And we have included, now you can actually sample these spin orbit couplings also at the QMC level, but here we have done a simple perturbative approach, and we have applied the DFT spin orbit couplings here. Okay, again, pre-screening by DFT, so you can see this is around minimum. You have, this is the minimum, you have K to K band gap, and if you go into compressive, you have K to K half, and in tensile, you have gamma to K, and you can see up to 4 lines here, which are the spin orbit coupling corrections, spin orbit splittings. Okay, this is how we calculated the 3 points, and we fit parabolas through that. Okay, so these are the results. So this is QMC, this is DFT again. So the results are quite similar. There is a rigid shift by roughly 1 electron volt, and here this is the gauge factor. So again, this is very similar indeed with the DFT. And now this is the QMC calculation. So as you can see, you can a little bit tune into the tensile strain. I forgot to say, tuning into tensile strain is important because that's what the experimentalists like, because if you compress, you may wrinkle the material and you may not be able to do what you desire to do. So tuning into tensile region is very important. But mainly we tune here into compressive region. Okay, so this is comparison with the DFT, PBE, DFT. They look very similar. What you see here is essentially a vertical shift downwards. All the band gaps are roughly an electron volt lower than in the QMC. In phosphorine, it was about 2 electron volts. The gauge factors also agree are quite similar. So the question is that valid for all transition metal dichalcogenides? I cannot answer this because we have done only one, but I believe that would be the case. And the question I can answer is, would that be in all the treatments? And for that reason, we have done a range of other calculations. So what I'm comparing here is our QMC with GW. There is a GW, that's now our calculation, but there is a GW result, and we have calculated the same in HSE, DFT HSE, and B3LA. So again, qualitatively, they look very similar. The phase diagrams, even the curvatures are very similar here. So everything looks very, very similar. Gauge factors look also very similar. However, and here is the main difference between these different treatments. For example, if I do GW, I would only be able to tune in compressive strain here. If I do then the study in HSE, I would be mainly tuning into the tensile strain, whereas in B3LA, I would be tuning exclusively in the compressive strain. So that's a very subtle point here, and I believe this type of calculation is a very sensitive criterion for accuracy of these calculations, and they can be actually used to judge the accuracy of the calculation you really have. Okay, so take-home message. I hope I have shown you that electronic and atomic structure of 2D materials can be studied using ultra-accurate fixed-node quantum Monte Carlo methods. In the materials I have looked at, the band gap can be tuned in tensile strain. Surprisingly, quintessential straintronic material MOS2 has tunability, which is an order of magnitude smaller than in phosphorine, and the tunability of phosphorine is colossal. And with that, I would finish the presentation and would thank you for your attention. Thank you.
Thanks, Ivan. So now the session is open to questions. You can ask questions directly through the Q&A box, or also through just by raising your hand, and you'll be given the floor. So I have already one question in the Q&A box. So there is asked by Pedro Ojeda May. He's asking whether the agreement between the FT-PBE and the Quantum Monte Carlo, I think he's referring to the first part, the phosphorine band gap, is accidental, or there is some theoretical background behind that.
Well, I do not dare to, yeah, I understand.
And then just to complete the question is, there is the second part of the question is about other DFT flavors, and if you can sort of rationalize the agreement or disagreement between these flavors.
Well, I mean, the agreement of the PBE is only in the ground state properties, right? I mean, the band gap is grossly in error. I mean, the error is there I mean, generally, PBE models very well the equilibrium properties, but the band gap is pathetic. I mean, it's 2 electron volt too small. And also the boundaries, I mean, the area where you have this gamma to gamma excitation is factor too small. So I wouldn't call that it's a very good agreement in part of the properties, but all the excited states are pathetically wrong. The hybrids, for example, do just the opposite. For example, B3LA would give you band gap, which is still a little bit too small, but is not grossly in error, but the equilibrium properties are very much in error, you know. So I would say these calculations could be used actually to sort of tune the DFT modeling, because you can actually always choose what models the desired property best. And the hybrids, I mean, there is infinite family of hybrids, because nowadays you can mix in as much exchange as you like. So you can cook up whatever you like. I mean, you may even end up with bandgap which is larger than experimental or QMC gap.
Okay, thanks. So there is another question by Kieran McDowell. So he's asking whether you can give more details about QMC calculations, the QMC method, and about the device, I guess the hardware, the machine where you, the HPC machine where you carried out the calculations. So it's about technicalities, but yeah, I agree that they're important.
Well, I mean, these are essentially standard QMC calculations. I didn't go very much in detail of that, but nodal hypersurfaces were fixed by DFT. So basically, we have linear functions which we calculate, and from that we construct our nodal hypersurfaces. Then we run the DMC over that. And that gives the only thing is, which is, I would say, not entirely standard, that we work in 4D space, which is a little bit tricky to do. We could actually minimize with QMC the internal parameters. We have tested that the cost is about the same. There is no huge saving of the CPU time if you minimize using QMC forces. We decided here to do this 4D in phosphorine paraboloids, and then go in minima in these two parameters, and then end up with a 2D paraboloid. So this the technical side. As far as the computations are concerned, most of these all phosphorine calculations were done exclusively on GPUs, on Marconi 100 in Cineca, and the efficiency was extremely high. Actually, the calculations were hardly touching the CPUs at all.
I just stopped you, Ivan, because I ask you to be very short, because we have many questions.
Okay, so that's it. Okay.
So yeah, but there is another question. I just take the opportunity, which is related to the the scalability and on the machines. There is a question about how the method scales with the problem size, and what is the largest possible size you can afford.
Well, these calculations are roughly the largest systems we have calculated are approaching 1,000 electrons. So that's the size, and yeah. So what else was the question? I got lost.
Yeah, the largest problem is 1,000 electrons, and the scalability.
Well,
the scaling with the system size.
1,000 electron is probably the upper limit we can do right now. I mean, we could actually plug in larger systems, but then there is a plethora of other problems which start to appear, which I don't want to go into. I would say 1,000 electrons is something you can currently.
All right, and then there are two other questions I just dare to merge because they are related. So the first one is about the accuracy of the fixed node approximation, so the fixed node error, and which is related, the accuracy also in the case of bilayer. So you presented monolayer calculations. In the case of bilayers, what is your expectations about accuracy? So fixed node approximation and accuracy in general.
Of course, I mean, if I have exact nodes, I mean, I can prove that I would have exact energies, which is never the case in these calculations because I have this DFT nodal hypersurface. But you have seen actually the DFT there is some truth in that because all these lines were very similar, etc. So I believe the accuracy is very high in these calculations. I would say I'm talking monolayers now. Okay, they are quite high, and you can, I mean, I have shown the comparison with the experiment, and we were like 600ths of an electron volt off with respect to the experiment. So that, I think, says it all. Bilayers are very different thing, really, because the problem there, I mean, let me put it very in a very simple way. In a bilayer, you have phosphorine is no problem because the bond is chemical, so phosphorine is very easy to calculate, bilayer or even the crystal, no problem. MOS2 is different because you have vacuum there. Once you have vacuum there, vacuum means empty states. Empty states means you can actually scatter into those states, and probably single determinant approach may not capture all the features which are needed. I mean, that's very simplified answer.
All right, so the last question, then we can switch to the next speaker. It's more sort of quantitative. So they'd like to know in what that's estimate in terms of GPU hours consumption in the case you are simulating a 1,000 electron system. What is the estimate you would give in this case?
Well,
on the GPU, on a GPU machine you mentioned?
Well, I mean, let me give you. I mean, all what we have calculated, the results I have shown here were roughly 50 million core hours. If I put it in terms of core hours, 50, 60 million, something of that order. It's very expensive.
But you know, for the full set of calculations, right? You know, it's,
all I have shown.
You have done many, right? Yeah.
And there are many actually,
yes.
And yeah. So yeah.
Okay, good. Thanks a lot, Ivan. So we need to move to the next speaker to stay on time. Yeah. So the next speaker is Katarina Doblov-Dier from Leiden University, and now we are leaving the topic of layered materials, and we enter in something different on surface physics. And the title of her talk is Barrier Heights in Heterogeneous Catalysis: The Good, the Bad, and the Evil. Please,
thank you, Michele.
The floor is yours.
Can you hear me and see the slides?
Yes. You should put on the slides. You don't see it yet.
They should be there. They're not. Let me try this again.
Yeah, now it's coming out. Good. Now we are going to see the PowerPoint interface, not the presentation screen.
Now it should be good, right?
Yeah, now it's the presentation mode. Yes.
Perfect. Thank you.
Thank you.
So indeed, I want to be talking about how we can use Quantum Monte Carlo actually to be specific to fusion Monte Carlo in heterogeneous catalysis. And as you'll see, it'll be a bit of story about the good, the bad, and the evil, but we'll get back to that. Before I start, I just briefly want to kind of introduce why we are interested in heterogeneous catalysis. I guess we also have physicists. So just to give you an idea, about 80% of our industrial chemical processes require catalysts, and most of those are heterogeneous. So that means we have some kind of surface, of, for example, a metal or an oxide on which a reaction occurs. And these processes do require incredible amounts of energy. In fact, if you just look at the Haber-Bosch process, it's estimated to actually use about 1% of world's energy consumption. So that's a lot. And clearly the idea of scientists, including also computational scientists, would be to improve these processes. So our dream in computational catalysis would be to have in silico catalyst design, in which we can design catalysts and reaction properties that require less energy and are thus greener. Now, the big question is, heterogeneous catalysis as such is actually already quite complex. So what can Quantum Monte Carlo do for heterogeneous catalysis? And if you say it's complex, I fully agree. There are a lot of processes that come into play that we need to actually take into account. For example, once we have these molecules that react on the surfaces, they can have many different configurations. And if we want to describe our catalytic process correctly, we actually have to take these multiple configurations into account. We'll also have several different reaction pathways, multiple intermediates and products. So again, that adds to the computational complexity of the problem. Once we have the energetics of our system, we still need to do the reaction kinetics, and sometimes that is not sufficient. We actually need the entire reaction dynamics in which we describe how our reaction proceeds on the kind of potential profile. To make things worse, we also have in case of electrochemistry, solvation effects, and we'll also have entropic effects. And because that is still not complicated enough, we also have the catalyst side. All these processes will depend on the structure and the composition of the catalyst, and that will actually change during operandi conditions. And finally, we need to take into account the entire nanostructure and flow profiles. So that is really incredibly complex. And in view of all these difficulties that we face, you can ask yourself, well, where would I need Quantum Monte Carlo? But in fact, none of these processes will we ever get correct if we do not get kind of the underlying principles right, which would be the electronic structure that allows to describe these different configurations, these different intermediates, and the catalyst structure. So the electronic properties of our system will remain really important. And clearly, in such a system, that there are several properties that we can be interested in, and I think each of those properties comes with its own difficulties. And in my talk here, I want to actually focus on barriers. And to be more exact, actually not only on barriers, but on a specific type of barriers, namely dissociative chemisorption barriers. Now, what is that? It's nothing else than a small molecule or any molecule coming towards the surface, then dissociating, and the dissociative products absorbing to the surface. Now, why would I focus on such a specific system? And the reason is simple. I want to learn something about the accuracy of our electronic structure methods. I really want to target kind of the real chemical accuracy, which is also what kind of brings me close to, in spirit, to the entire TREX idea. If we try to figure out how good our electronic structure method does by trying to compare with real catalytic systems, I think we won't get there. You just saw this entire complexity that comes into play. If we really try to simulate a real catalyst, we won't be able to do that. So we do need model systems, at least at the moment, where we still need to learn how things work. And these dissociative chemisorptions are, I think, ideal candidates. For one reason, these dissociative chemisorption are often rate limiting. For example, in the Haber-Bosch process, it would be actually the splitting of an N2 molecule into two Ns that is rate limiting. On the other hand, for these systems, one can perform very accurate experiments where molecules come in with a certain probability distribution of velocities in a molecular beam, and we can measure very exactly what dissociates and what doesn't. Also, these barriers, in particular for these heterogeneous catalysis, are really a difficulty for today's computational descriptions. In heterogeneous catalysis, what happens most of the time is that people perform density functional theory calculations, and actually density functional theory calculations on the level of the general gradient approximation or anything that might build on it, so maybe mixed with van der Waals correlations. But DFT will very likely struggle for this composite system of molecule and metallic surface. And the reason is very simply that they have very different properties. In a molecule, my electrons are relatively localized, while in the metal, they are very delocalized. And that translates also in different requirements for the exchange correlation functional. We know that for molecules, in particular, if you want to describe barriers, the functionals will profit from very strong long-range exchange. While in metals, typically we try to turn long-range exchange off because it shouldn't be there, because it's shielded by the electrons that can move around in the metal. So that makes it already a difficult system. Additionally, because it's very hard to measure anything for these systems, we have virtually no training data on which we could kind of benchmark our functionals on. So the quality of DFT, you can already imagine, might suffer. And you can see that very easily here on one particular reaction barrier here for H2 dissociating on a copper surface. I show the results for the lowest lying barrier for different functionals. And even if we choose two kind of reasonable functionals, PBED2 would be often used in electrocatalysis, RPB van der Waals CF, maybe more in gas surface science, but they lie 0.7 electron volts apart. So they predict a barrier that is 0.7 electron volts different. Now, considering that the entire barrier is only 0.6 electron volts, I think that's an important difference. And even if you take functionals that lie much closer to each other, this directly translates in a very strong change in reaction probability. So we'd really like to get these barriers correct if we want to be predictive. So considering that this is a QMC conference, the obvious question to ask is, can the fusion Monte Carlo do better? And what I'm plotting here is actually two barrier heights for two different systems, H2 dissociating on a copper surface and H2 dissociating on an aluminum surface. In blue, you'll see different DFD calculations, all either GGA functionals or meta-GGA functionals or GGA functionals with van der Waals correlation. And none of them kind of gets the barrier for both systems correct. Hybrids seem to do a bit better, in particular if we add higher amounts of exact exchange, which might be expected based on what we know from gas phase, where also increasing the exact exchange improves the description of barriers. But DMC still does considerably better. And actually DMC gets us already very much into the range where we'd like to be, which might be this kind of inner circle, which is 40 MeVs, or what we in chemistry often call chemical accuracy. So we are getting there with DMC. And that's good. He's my good guy. There's also a bad guy, and that is the problem of computational cost. Getting these points might cost hundreds of thousands of CPU hours. And clearly, if we then try to describe our entire catalytic process, including all the difficulties that I sketched in the beginning, having costs of hundreds of thousands of CPU hours for a single point is not really acceptable. So we need to find a strategy in which we can use this information, but get rid of the computational cost. And to understand how this works, I want to focus on one of the two systems that I just showed, namely the H2 and aluminum. And what I'm now showing are several different barrier heights for the same system. And what you can see is, okay, PBE might get it pretty wrong. We are off by about 6 kcals per mole, which is a lot. But if you look at the trends for the different barriers, in all cases, these functionals seem to behave similarly. And we could have done that for more systems. We always observe the same trend. So as long as we are in one system, apparently DFD gets trends in barrier heights, in different barrier heights, even if they are on strongly different geometric sites on the surface. Even then we get them more or less correct. We can try to quantify this a bit better. So here I plot, instead of 3 barriers, actually 6 barriers. And we are looking at here at the corrugation and anisotropy of the barrier. So there's nothing else than how does the barrier change compared to the lowest lying barrier. And then I compare this corrugation and anisotropy to that had been predicted by DMC. And you can see that the predictions compared to DMC never differ by more than 2 kcals per mole for all the functionals tested and for all the barrier heights shown here. So again, that shows that the trends in different barrier heights seem to be described correctly. And all we need is to find a functional that actually gets kind of the absolute barrier height correct. And that is where the entire idea comes from, to kind of marry the fusion Monte Carlo to density functional theory, in order to then maybe get to a description in which we can predict sticking, that is a synonym for dissociative absorption here, at the chemical accuracy. So the question is how to marry density functional theory and quantum Monte Carlo. And here we just used a very, very pragmatic approach. We mixed RPBE and PBE exchange. So there's nothing else than scaling this gradient enhancement factor in our functional and added van der Waals correlation. Then we took the barrier height that we got for the lowest lying transition state in DMC and tried to kind of scale A such that we would find a functional that here I call QMC-based density functional that closely reproduces this barrier. And once we have this QMC-based density functional, we can try to ask the question, well, can we now use this to correctly predict our sticking probability? Now, in doing so, there's still, for this particular system, one difficulty that we have to take into account, and that becomes obvious if you look at this graph. Each and all of those incidence energies, and actually not one particular incidence energy, it's just points kind of the average incidence energy. So we have a molecular beam with an entire beam distribution, and we have to describe all these different possible kind of initial conditions of our molecule coming to the surface and predict for each of them whether it might react or not. The other thing that you might notice is that the sticking probabilities are really low. So if you think in a brute force way, if we have a sticking probability of about 10 to the minus 6, we would require at least 10 to the power of 6 trajectories. It's not quite true because some of the trajectories we don't actually have to propagate because we already know that they have too little energy to actually overcome this barrier. But also modo, this is kind of the way to think. Each of these trajectories needs about 10 to the power of 3 steps or something alike. So here we would end up with it thinking brute force, 10 to the power of 9 DFT calculations that we have to perform to propagate each and all of these trajectories and predict a sticking probability. Now, even if we apply the tricks that I just said, that we don't have to propagate all of them, this is still out of reach computationally. So we have to actually use a surrogate model, a surrogate machine learning model. So we fitted a machine learned potential to data that we can now obtain from the QMCDF. So we get a few thousand points from the QMC-based density functional, and we train a machine learned model. And again, we get the barrier height for the lowest lying transition state reasonably well. The difference between the DMC, again, remember this now gives an entire potential energy surface, while this is a single point. And we can take this entire potential energy surface to do the dynamics, and these are the results here. Now, the results that I'm plotting here are actually obtained keeping my surface fixed and using the von Oppenheimer approximation. You can say, okay, that is a bad idea because actually aluminum is not that heavy and hydrogen might actually kick on the aluminum and lose some energy to react and something might happen. So we can go a step further and allow the surface to move. You'll see the reaction probability decreasing a bit. You can rationalize this by energy lost towards the aluminum atoms. You can also say, I don't like the von Oppenheimer approximation. How about non-adiabatic effects? And that is a valid point because in the metal you have these the kind of states close to the Fermi energy, so you can have infinitesimally small excitations of electrons, and that could lead to what we call electronic friction, which is basically nothing else than a non-adiabatic effect in which we could lose energy. We can try to include this electronic friction, gives us the yellow line, nothing much happened. I'd actually say it's basically within error bars. Lastly, you could also say, well, H2 is actually not very heavy, so how about quantum effects? So you can try to approximately correct for these quantum effects. It has an influence mainly at the low incident energies, which might be expected because that is the region where tunneling should be important, while up here it doesn't do much. So now we can take these results and ask, okay, how well did we actually perform now? Is this good or is this bad? And for this, you actually need to look at kind of the shift that we have in this predicted reaction probability line compared to the experimental reaction probability line. And we are off by about 1.4 kcals per mole. And somehow this suggests that the entire potential energy surface is kind of in the barrier heights is shifted by 1.4 kcals per mole. So is this the DMC barrier on which we based our potential energy surface that is 1.4 kcals per mole off? Now that's not immediately obvious, in fact, because the second lowest lying transition state is very close in energy. It's about 1.5 kcals per mole higher if we believe the DMC calculation. So this would be the location of the transition state 1. The molecule dissociates over the long bridge site, and this is the location of the transition state 2. The molecule dissociates over the short bridge site. So this is the DMC predictions for these two barriers. But our QMC-based density functional gets the first barrier pretty well, which is the one we fitted it to, but the second one it underestimates. So maybe that is the reason why we overestimate the experimental reaction probability curve. But in fact, that is not the reason. We can test that. We can basically split our entire reaction probability curve into the components of molecules reacting here or molecules reacting there. And we can see that the molecules reacting here, so along TS1, are more important. And we can also rationalize this by looking at what we call elbow plots. So these elbow plots are nothing else than a cut through the potential energy surface along kind of these cuts here for the molecule coming closer to the surface and the molecule stretching along its kind of geometry at the transition state. And here is plotted the minimum energy path as well as the transition state. And you can see that for transition state 1, this barrier lies much more within a region where the vibrational motion of the molecule is important to actually bring you over this barrier. Taking into account that the incidence energies, the average incidence energies of this beam are much lower than the barrier height itself, we can already imagine that vibrational excitations in these beams will be important. And we can use the energy of these vibrational excitations much more efficiently to overcome the barrier in transition state 1 than in transition state 2. Which then leads to the fact that transition state 2 has a small influence on whatever shift we observe here is very likely indeed a shift that is due to the diffusion Monte Carlo barrier to be slightly too low. So in summary, what I have shown you here is that you can actually fit or choose a density functional theory to match very scarce DMC data, but even that may allow you to get predictive results for dissociative chemisorption. We can also then compare whatever we had in the prediction to experimental reaction curves if they are available, and that might give us information on the accuracy of DMC. And in this particular case, I think the accuracy of DMC is about 1.5 kcals per mole, and that is similar to what we find for H2 on copper. We also think that their DMC results are off by about 1.5 kcals per mole. This approach up here, I think we can still improve by using delta machine learning. We could maybe use several DMC data points and then just get a delta learning model to improve over the DFT results. And because the differences should be kind of slowly varying, this should be an approach that should converge pretty fast. Now, there is a difficulty still with this approach sketched up here, that where we can choose a density functional theory to match DMC. And that is that there are actually reactions in which there is no GGA functional that will be able to match the experimental or the DMC barrier. And in fact, an observation that we have made is that this seems to happen whenever the work function gets close to the electron affinity of the molecule dissociating on this metal. And if you were very careful in the beginning of the talk, you might have actually already have seen this happening. When you show this plot here, this is again the barrier for H2 on copper, and you can see that the different density functionals shown in blue scatter around what we believe is the true value. While for H2 on aluminum, all the functionals that I showed here underestimate the barrier. So there's a clear incorrect correlation that the DFT data follows. Gets improved when we use the hybrids, but DMC is even better. So if ever we want to have this kind of method work where we kind of choose a density functional to match the experimental values, somehow we still need to solve for these systems in which no functional gives a high enough barrier. And to do so, I think we need to really get at the origin of why the density functionals underestimate these barriers. And from this plot, you can already see that the issue is not in the gradient enhancement factor. As we go from PBE to RPBE, okay, the point moves, but it will not get us up here. It goes along kind of this scaling. Also, if we add dispersion corrections, again, we might go from PBE to PBE by the Waals dn, but it does not bring us outside of this correlation line. So this cannot help us. What we note, however, is that hybrids somehow help, and often this has something to do with band alignment issues. So that could happen if the LUMO, for example, moves under the Fermi energy of the metal and is incorrectly populated. Now we can check whether that happens, but to do so, actually, what I did is go a step further and also do an RPA calculation for the same two systems. First of all, you'll notice that the RPA and the DMC calculations both cluster around where we expect the correct barriers, so that's good. They also agree relatively well with each other, so it's also good. But we can also use these RPA calculations or then the GW calculations to look on whether band alignment is an issue. And based on these results, I actually don't think that it's really a band alignment issue. If you plot kind of the population of the hydrogen-related density versus the total density of states as we cross Fermi, independently of whether you use a GW calculation shown here in dark green for the hydrogen-related density of states and the total density of states in black, or whether we use a DFT calculation for the same, the population on the hydrogens doesn't seem to change. So I don't think that this is a band alignment issue. But still, something happens with the exact exchange. Whenever we turn on strong exact exchange, things get better. So the obvious candidates to look for might be density-driven self-interaction errors or energy-driven self-interaction errors. And from other calculations in literature, we actually know that going from a hybrid calculation to a non-self-consistent hybrid calculation in which we use the density from a DFT calculation, but then just form a hybrid calculation on top, at least for O2 reacting on aluminum, doesn't help. So it doesn't seem to be a density-driven self-interaction error, because otherwise the self-consistent or non-self-consistent calculations would differ a lot. So the bad guy here seems to be energy-driven self-interaction errors. And I think that is an important take-home message, because it could also tell us how we can improve these density functional theories maybe in the future. So taken together, I hope that what I have been able to show you is that using DMC calculations allows us to have predictive results by matching to a single value, and maybe in the future by matching to a few tens of values by using delta machine learning. We can then also use the DMC data to actually provide benchmark data to kind of tell us something about the DFT calculations here, and train DFT calculations maybe better. And finally, in the combination of DMC and RPA, which kind of correspond quite nicely, we can also try to learn something about the shortcomings of the JGA functionals. And as I said, I think that the evil guy here might be energy-driven self-interaction errors. Now, before I stop, I'd like to thank the people involved, in particular Gert-Jan Kroes, who's the mastermind behind the dynamics calculations. Also, all the students, which are actually Gert-Jan's students, and with whom I could also, at least in part, work to kind of get this project done. Also, Benjamin Odoa, former master student, who did lots of the calculations for the RPA that I showed. I'd also like to thank my group, who are actually mostly not involved in these calculations, because most of them now do electrochemistry. Also Mark Kopa, in whose group I'm partially involved, as well as other external collaboration partners. And with this, I'd like to thank you for your attention.
Thank you, Katerina. So we have several questions again on the Q&A box. So one of them, let's start from the again a question about computation time. So how long it takes to run your DMC and Quantum Monte Carlo density functional on the cluster for the case study you have presented?
Yeah. So for H2 on copper, that were a few million CPU hours for a single point. For H2 on aluminum, that were a few hundred, few 100,000 CPU hours per point. So we could also then describe several points, which I think for H2 on copper would not have been possible. But these are also, keep in mind, these are really big systems. So I think that maybe if I briefly go to kind of the system size. So this is the system size that we have for H2 and aluminum. We need an incredible amount of layers to get this converged, otherwise we just have an error. And this is the smallest supercell that we considered. But then from there, we actually do finite size extrapolations over here from this supercell that you just saw to actually a supercell that's twice as big, so that has 4 by 4 by 10 aluminum atoms in the surface, and then extrapolate to infinite size. So all of this is included in these several 100,000 of CPU hours, including also, in fact, the twist averaging, which for these metallic systems is very important. What we do is for the 2 by 2 cell, so that is 2 by 2 by 10 aluminum atoms, we use basically an 8 by 8 K-point grid. We use all the symmetry inequivalent K-points, which gives us 32 K-points. For the 4 by 4 cell, it's 8 K-points that we consider. So again, this has to be taken into account in the computational time.
Yes. So just a question again on the DMC. It's about the question on DMC and these transition state geometry, TS geometries. So are the geometries taken from DFT structures, or they're optimized at the DFT level?
Yeah, that's a very good question. No, they are actually they are taken from DFT with a certain trick. And the trick is that we know that DFT typically gets lattice parameters wrong, and that this can have an important effect. So we expect QMC to actually get the lattice parameters correct. So we take the lattice parameters and the interlattice, so the surface interlayer distances from experiment. We extrapolate to 0 Kelvin. We build our kind of experimentally motivated metal surface from there. And then we take the transition state geometry as we obtained it within DFT and kind of copy that onto our new metal. So it is a transition state geometry that is taken from DFT and a slab geometry that is taken from experiment.
Okay, thank you. And then if we move to the machine learning part, there is a question about the type of training and validation time, the method and the validation time for the machine learning model.
The validation time, I don't know. What we did is to use a Bailot-Parinello type of kind of machine learning model, so that allows you to be rotationally invariant in your system. and splits the total potential energy total potential energy into kind of atomic contributions. We trained that originally from kind of just kind of testing or computing several DFT values that we know will be energetically relevant. So within the space of DFT, where we know that we have energetically relevant data, and we do improve that typically when running, whenever we see that there's an issue happening, that we run into kind of regions in the potential energy surface that we have not properly included in the training data. We see that, and we can fix that a posteriori.
Okay, thank you, Katharina. So now we need to stop because we have a coffee break scheduled, and there is no more time for other questions. I'm sorry. So we'll resume in a couple of minutes. So it will be a very short coffee, intense coffee. Yes, so thank you again, and I'll see you in at 10:50.
Thank you.
Thank you. So after a very short coffee, we resume the webinar. So for those connecting and joining now, I remind that this is a jointly TREX and CECAM webinar covering different aspects of condensed matter physics, quantum chemistry, and material science. And we have seen topics on layered materials and surface physics this morning, and we will move to magnetism, excitations, and high pressure physics in the next 3 talks. So I have the pleasure to introduce to you Ali Alavi, who's the next speaker, and he will talk about some peculiar features of spin adaptation in quantum chemistry, why orbital ordering matters. Ali, the floor is yours.
Okay. Thank you, Michele. Let me just, first of all, share my screen. Okay, is that full screen mode for you?
Yeah, it's perfect.
Okay. Okay, thank you. I'm going to talk about a finding which I think is quite general, actually, concerning properties of spin eigenfunctions, or sometimes these things are called configuration state functions, which are used in CI expansions of systems that contain many open shell electrons. And these are typically systems which are extremely non-compact in their description, so they require many CSFs to get a good description, even qualitatively correct description of the wave functions. And with this trick, we find a way of drastically compactifying these, and that much eases the ab initio description of these systems. Okay, but by way of introduction and the type of systems that we're interested in polynuclear transition metal complexes. I show here an iron-sulfur cubane, which typically consist of multiple transition metal sites, which are typically magnetic sites, so that they locally have a magnetic moment, but which are typically spin coupled into a low spin structure, or a low spin wave function. And the part of the construction of these molecules involves ligands which bridge the transition metal sites, and which actually are part of the effective magnetic interactions between these sites. So in biology, there are examples. There are iron-sulfur complexes. There are manganese oxygen complexes in photosystem 2. In nitrogenase, you have this very large complex, FIMOCO, and so on. And it's interesting that these molecules are implicated in biology, both in electron transport. So electrons can hop on and off these systems, as well as in catalysis of spin-forbidden reactions, such as water splitting. Okay, so the challenges involved, as I mentioned, is that although the magnetic systems are typically high spin, so for example, if you have an iron 3 center, locally speaking, each ion will be in a spin 5 halves configuration. The overall spin of the system is low. And these are examples of extreme multi-reference systems as defined in quantum chemistry, which means that to get even a qualitative description of the wave functions, you require many, many CSFs to describe them. And the systems are typically strongly antiferromagnetic. And this antiferromagnetic coupling is induced by various exchange and super exchange mechanisms that involve the ligands. The cubane structure turns out to be a motif that occurs repeatedly in these systems, and that in turn implies that there must be frustration among the magnetic interactions. So you cannot simultaneously satisfy all the antiferromagnetic interactions, and that leads to frustration. And the frustration itself then leads to typically very complex low energy spectrum with small gaps, small energy gaps between states of the same low spin and indeed between different spins as well. And these are hallmarks of strong electron correlation. And finally, the structures of the molecules are nearly always distorted, and these are indicative of Jahn-Teller effects. And the nuclear dynamics is quite possibly non-adiabatic as well. And what we want to be able to understand in these systems is at least two levels of description. On the one hand, we want a detailed ab initio description, so basically starting from the Schrödinger equation and getting an ab initio description, let's say, of the energy levels of the spectra. But in fact, just getting numbers out of what are going to be extremely heavy, detailed, complicated calculations doesn't lead to a whole lot of understanding. And so the other thing that we want to be able to do is to relate how the ab initio description can be reproduced, if you like, can be modeled in terms of, let's say, much simpler phenomenological models, such as spin models. For example, Heisenberg model, which is appropriate for these types of systems, and extensions of the Heisenberg model, which go beyond, let's say, SI.SJ type of couplings. But the main point about these is that when we write Heisenberg models, we have some exchange constants, these, let's say, JIJs, and let's say higher order exchange constants, which have to be then obtained from ab initio, and then they can be compared with experiment. And the typical energy scale of these exchange constants is only on the order of, let's say, tens of milli-electron volts. So that, if you like, sets the energy scale and hence the challenge involved. Okay, now I mentioned that, these systems are extreme examples of multi-reference systems. And we need a way of measuring multi-reference behavior. And that can be measured through the concept of spin degeneracy. And spin degeneracy is essentially the number of ways you can construct spin eigenfunctions. So these are orthonormal spin eigenfunctions for a system consisting of a certain number of open shell orbitals, so orbitals that consist of only that are only singly occupied, for a given spin. And the spin degeneracy can be worked out on the basis of this, this combinatorial formula. It's called the Van Vleck-Sherman formula, and this basically tells you the number of spin eigenfunctions that you actually need in order to describe the ground state wave function. That's the minimal number that you need. And to give you an idea of, first of all, where this formula comes from and what it actually implies, you can actually obtain these from a spin branching diagram, where on the x-axis you have the number of open shell orbitals, and on the y-axis you have the spin, and you can construct these spin eigenfunctions in so-called genealogical way, where you start off by putting the first electron in the first orbital, and that takes you to a spin half system. And then the second electron, which goes in the second orbital, you can either spin couple positively to get a triplet or negatively to get a singlet. And you can see that the first example of a spin degeneracy occurs when you have 3 electrons and you want to construct a spin half wave function. That gives you a spin degeneracy of 2, which basically means that you can either go up to a triplet and spin couple down, that gives you 1 spin eigenfunction, or you can take a 2-electron singlet and spin couple up, and that gives you a second CSF. Now, of course, if you've only got a few CSFs, that in itself isn't a problem to deal with. But if you have, for example, these ion cubane systems, each ion has, say, 5 open shell 3D electrons, and so that in the cubane leads you to 20 open shell electrons. And then you can see that according to the spin branching diagram, the ground state wave function of that system would consist in the spin 0 case of over 16,000 CSFs. And that means that there are over 16,000 leading terms in the CSF. That's just to get a qualitatively correct description of the wave function. That's before we've even started to describe the dynamical correlation in the system. And of course, each one of these CSFs itself consists of many numerous slated determinants. And so you can see these problems get out of hand very, very quickly. And with the state-of-the-art standard quantum chemistry, the maximum that one can treat are 18 open shell systems with 18 open shell electrons. Okay, so now I'm going to digress a little bit and explain a very interesting, or at least I find interesting, finding regarding these spin eigenfunctions. And to illustrate what's going on, let's look at the 3-electron system, 3 electrons and 3 orbitals, which, as I mentioned before, that space is spanned by 2 CSFs, up, up, down. So this is where you spin couple the first 2 electrons to get a triplet, and then a 3rd electron, spin couple it down, or up, down, up. And these 2 CSF have a standard slated determinant expansion in terms of the primitive spin functions. So these are, these are well known. You can look them up in the textbook, and that's what they are. Now, the point about this is that when we write this, we typically assume that we're going to spin couple the electrons in natural order. What that means is that we put the first electron in the first orbital, and then the second electron we put in the second orbital and spin couple it to the first, and then we spin couple the 3rd electron. And that produces us a naturally ordered CSF. Okay. But now let's consider doing something which initially seems a bit odd, which is let's apply a permutation operator onto one of these CSFs. And the particular permutation operator we're going to consider is P23. So we're going to swap the labels of sites 2 and 3. So when you do that, you generate, so you apply that, let's say, to one of the CSFs, U1, U2, D3, you generate a CSF U1, U3, D2. And that means that in the construction of this CSF, you put the first electron in the first orbital, then you spin couple the electron on site 3, that comes second, and then you spin couple the electron on site 2. And if you do that, you end up with a different spin eigenfunction, which can now be re-expressed in terms of the original spin-ordered, the two naturally ordered spin eigenfunctions. And you can see that this thing itself now spans actually the two naturally ordered spin eigenfunctions. And you can do the same thing applying this P23 permutation operator on the second spin eigenfunction. And that also generates you now a different expansion. And when you look at these, you actually realize that the action of permutation operators is to generate unitary transformations of the CSFs among themselves. Okay, now why is that interesting? And it's interesting for the following reason, is that if you look at now the Heisenberg Hamiltonian, and you consider and you express the Heisenberg Hamiltonian in the original naturally ordered CSF basis, you end up with a 2x2 matrix that's shown here. And now you have to diagonalize this to get the eigenfunctions and the solution of the problem. However, most interestingly, if you express the Heisenberg Hamiltonian in this 1-3-2 basis, where you've permuted the two labels, you actually find that the Heisenberg Hamiltonian is already diagonal in that basis, and you have nothing more to do. So in other words, we've discovered a unitary transformation, which is just a pure reordering. You've actually managed to diagonalize this Heisenberg problem. So that's, we found that as really quite interesting. And unfortunately, and not surprisingly, this doesn't generalize beyond 4 sites, actually. 4 sites also turns out to diagonalize the Heisenberg Hamiltonian, but for longer chains, this doesn't happen. But nevertheless, we find that we're able to compactify the description through this reordering trick. So if we look at a 6-site problem, so which we can either do looking at a linear chain here, or with periodic boundary conditions that you can sort of think of as a benzene molecule, then you find, for example, in the periodic boundary condition case, that if you take a naturally ordered CSF basis, that the leading term in the ground state wave function is about 78% dominated by one CSF. But in this case, we could do an exhaustive search over all possible the 6 factorial permutations. We found that there is another representation that we call the compact representation, in which that single CSF actually represents over 97% of the wave function. So we're able to, push the leading CSF from about 78% to over 97%. And interestingly enough, the optimal ordering that we find looks like this: 1, 3, 2, 5, 4, 6, which means that we start off by placing the first electron on site 1, and then the second electron that we couple is this one on site 3, then we move back to site 2, and then 4, 5, 6, and so on. And that, what looks like a peculiar ordering, actually leads to this extremely compact description. So what is actually going on here is that this ordering that we find actually amounts to propagating a doublet metaspin down the chain, almost like a soliton. So you can see that if we spin couple the first three sites in the manner that we discovered with the 3-site problem, the 1, 3, 2 chain, we get another doublet. We call this 1 prime. That can then be now spin coupled to the next 3 sites, and so on. And that ends up propagating this spin half doublet down the chain. And one can recursively construct enormous spin eigenfunctions consisting of very large numbers of open shell orbitals in this way. And we find that even going to really very, very long chains here, this is a chain consisting of 80 sites. So, that would be a Hilbert space of 2 to the 80, which is absolutely enormous. We find that this single CSF accounts for over 50% of that wave function. Okay, now you might ask, well, what is actually the physics behind this? Why does this actually work? And this essentially, this reordering trick is enabling us to introduce correlations, spin-spin correlations between distant pairs of electrons in such a way as to mimic the exact spin-spin correlation. And so that's shown here, where the exact spin-spin correlation function is shown in blue. So what that means is that we fix the spin on one of the sites and look how the other spins correlate with respect to it. And you can see that the naturally ordered CSFs lead to a very rapidly decaying spin-spin correlation, so that essentially you have nothing left beyond the second site. Whereas this compact ordering actually enables us to really mimic very closely for quite some distance the exact spin-spin correlation. So this now brings me to the topic of ab initio, because you might say, well, okay, this trick of reordering, that worked maybe for model systems, but what about actual ab initio systems, which are the systems that we really want to describe? And so we use spin adaptation in the context of ab initio, using the so-called unitary group approach, or the graphical unitary approach, which is just one way of performing spin adaptation. And we've combined that with the full CIQMC method, and that's work that it's actually fairly old now, going back to 2019. And I won't have time to describe that, but the key feature that nevertheless remains in either Guga or other spin adaptation methods is that one has to make a certain choice of how you order your orbitals, your spatial orbitals that are going into the description of your system. And here we can now take an ab initio. This is a model ab initio system to explain what is going on. So here we take a system of 4 nitrogen atoms, and each nitrogen is itself in a high spin state, so is in a spin 3/2 state. That's what nitrogen, the N atom is. And we construct now the Hamiltonian matrix in this unitary group formulation. The details need not matter. Using 2 different orderings of the orbitals. Now, in one ordering, which is actually the one that you would normally use, would be that we put all the px orbitals of the 4 nitrogen centers first. And the reason why you do that is because you can then spin adapt you can spatially adapt by forming space adapted linear combinations of these px orbitals together. So here we have the ordering where we put the px orbitals first, then the py orbitals, and then the pz orbitals. And if you look at the corresponding Hamiltonian with that ordering, you get this rather dense Hamiltonian. If, on the other hand, you choose a different ordering where you first of all order all the orbitals on, let's say, one of the nitrogens, nitrogen A first, then the orbitals on nitrogen B, then the orbitals on nitrogen C, and so on, you end up instead with the Hamiltonian that's shown on the right, which is basically block diagonal. You can see that. And obviously, it's going to take much less effort to diagonalize the Hamiltonian on the right compared to the Hamiltonian on the left. So now we can actually use this trick in not just in this model system for isolated nitrogen atoms, but in actually these real systems, the iron sulfur complexes that we want to look at. And so each ion consists in its minimal active space of 5 3D orbitals. So here, this is the 3D orbitals shown on one of the ions. So there's going to be 4 sets of these, as well as the 3p orbitals on the sulfur ligands. That will then enable us to generate these, let's say, minimal active spaces to describe these iron sulfur complexes. Now, one thing I should point out is that when you look at these cubanes, you see that there are distortions, and there are typically 2 distortions that are relevant. Those which lead to 2 long and 4 short bonds among the distorted tetrahedra, or vice versa, 4 long and 2 short. And which distortion then occurs in practice then depends on the ligands and things like that. Okay, but as I mentioned before, because these iron sites are themselves antiferromagnetic, you end up necessarily with geometric frustration. And how much do I have, Michele?
Well, I mean, just a few minutes.
A few minutes, okay. Yeah, I'm actually more or less done.
Yeah.
The minimal number of in the minimal active space, you require something like 10 to the 10 Slater determinants to describe the wave functions, just correlating the 3D electrons. And if you consider the sulfurs, that goes up to about 10 to the 15. So these are really very large active spaces. But we find that with the appropriate ordering that we actually showed, we can actually drastically compactify the solution essentially in the ground state down to a single CSF. And we looked at a manifold of singlets, including 5 excited states. And actually, interestingly, the 5th excited state can also be described essentially by a single CSF. The intermediate ones have got a larger number of CSFs. So what we've actually shown is that through this reordering trick, we can drastically compactify, let's say, what is required to obtain a qualitatively correct description of the ground states. And you can rationalize that in terms of these spin branching diagrams. So everything turns out to be very consistent. Okay, now we can use the ab initio data to come back and actually fit to a Heisenberg model and extract the corresponding exchange constants. And for one of the compounds for which there are actual experimental measurements, we find that an active space that only consists of the iron produces not very good, well, reasonably good, but not perfect values for the exchange constants. But when we actually now correlate also the sulfur ligands, we get a really pretty good agreement with respect to experiment. And what's actually particularly interesting is that we don't just get absolute agreement in terms of the constants, but also the relative agreements. Nevertheless, the difference in the J's also comes out very well. And finally, one can now fit the spin ladder of these complexes, so over multiple spin states. And to cut a long story short, we can actually show that a simple Heisenberg model ends up not being a very good description of the full spin ladder, but one has to extend it to these biquadratic terms. And then at that point, we do get a very good description. Okay, so let me just conclude that this orbital reordering trick that we've discovered is really able to induce enormous spin compactness into these spin-adapted wave functions. And many previously considered multi-reference systems can actually be rendered essentially single reference in this way. However, the extension of these methods beyond active space calculations remains extremely challenging. And that's actually what's consumed most of our work, is to extend now, to extend the transcorrelation framework to these types of systems. But that is still work that is ongoing. Okay.
Okay, thank you a lot, Ali, for this nice talk. So the session is open to questions. You can either use the Q&A prompt, or you can raise your hands. So there is no questions yet. I have one. So you mentioned about these the Google features of reducing the complexity of the underlying Hamiltonian. So you get a Hamiltonian which looks more diagonal, so to speak, so easier to diagonalize. In the context of Fusei Quantum Monte Carlo, what is the benefit of doing this? So I understand this in terms of ED, diagonalization, but in terms of Fusei Quantum Monte Carlo, is there any? Yeah,
there's huge benefits, benefits.
Yes.
So FCI QMC works best when the wave function is basically dominated by one CSF or one slated determinant, or a few. But whenever you have wave functions where you have many leading terms, those are actually very problematic, even for full CI/QMC. So you end up with enormous fluctuations in the energy and things like that that are very difficult to kind of quench. So even within full CI/QMC, you want to get as single reference a wave function as you possibly can. So you can see it actually, these are the actual simulations, and you can see that when you have a very single reference wave function, you've got practically no fluctuations in the energy, and things work extremely well. So, this is a basically win-win all the way. And I believe it'll be win-win for other methods as well, outside of full CI/QMC, like selected CI. And probably if you want to do DMC using these types of CSFs, obviously having only one CSF rather than multiple CSFs is going to be an enormous gain as well. So, I see this as being very helpful, across the board.
So it can be used also across different QMC methods, not only full CI.
Indeed, absolutely, right. Absolutely.
So there is another question by Sasha Lichtenstein. Is wondering about comparison against matrix product state methods, MPS methods. So how this compares against the MPS?
So this is actually a very interesting question. I mean, we've looked at this in this paper. So it turns out that the orbital ordering that we need here is different to the orbital ordering that's needed in DMRG. So in other words, if you take the optimal ordering that you get from, let's say, DMRG, it turns out not to be the most compact from this perspective and vice versa. So it's doing a different thing, in other words. So in DMRG, you're trying to produce minimally entangled wave functions. Whereas here, it appears that what we're trying to do is to, within a single CSF, mimic the long-range entanglement through this reordering trick. So there seems to be some relation to what's going on in these matrix product methods, but it's not the same thing at the same time. Yeah. Okay, good. There is a last question before going to the next talk. By Silke Biermann. Concerning slide 16, may I interpret the optimal order naively as some kind of locality of correlations? Correct, yeah. Yeah, so that's one thing, but it's not the only thing, however. I mean, in this case, it turns out to be the case. But when you're looking at these more complicated problems, you know, it turns out that whether you spin couple across a bond, which is antiferromagnetic or ferromagnetic, is also important. So yes, definitely the locality is important, but then the locality with respect to neighboring sites is also important. And that one we haven't fully worked out yet, actually, how to go about you know, getting the optimal ordering in more complicated situations. So we're working on that, yeah. Okay, thank you, Ali, for this fascinating talk. And we'll have to move to the next speaker, who's Claudia Filippi. We have seen her at the welcome message part of the webinar. So now is the time for her to talk about the topic of energy excitations, in particular excited state calculations in Quantum Monte Carlo.
It's good, it's in full screen?
Yeah, it's in full screen, yes.
Very good. Okay. Okay, thank you, Michele. I will discuss some work we have been doing in the last few years about computing excited state properties using Quantum Monte Carlo. Right? And here we're going back to real space Quantum Monte Carlo, like the two first speakers actually used. Okay, so now what we are trying to do is we're trying to see how well we are doing using Quantum Monte Carlo to describe excitation energy. Okay, so we really want to establish the method as a reliable option. Okay, so first of all, indeed, we start from absorption, so which is already complicated, and by this we mean vertical excitations of relatively small molecules. Okay, so we start with thiophene here. Thiophene is quite small, is a pi to pi star excitation, what I'm looking at, so quite simple. And what I'm showing in this plot is actually, they're all correlated methods. Okay, so the scale is 0.5 eV, which is quite large. On this side, I have a multi-reference PT2, I have CAS-SCF, CAS-PT2, NEF-PT2, and you can see quite some spread. And here is Quantum Monte Carlo, and Quantum Monte Carlo, there are 4 points. You know, so one is variational Monte Carlo with some wave function, the corresponding diffusion Monte Carlo, variational Monte Carlo with a better wave function, and diffusion Monte Carlo. And so we are also seeing a dependence. And couple cluster, this is CC3, is a couple cluster single, double, and approximate triple, let's say, and is considered to be quite reliable for this molecule. Okay, so this is, there is no DFT here, so this is only many body, and the spread is quite dramatic, okay, and the situation is not unusual. So because of this difference among, methods which are supposed to be, very accurate, there's been really a search of benchmarking for excited state, mainly by the group of Pierre-François Loos and Jacquemin, and they mostly focused on absorption and fluorescence, but then they really used, full CI, extrapolated, full CI, couple clusters, single, double, triple, and quadruple, and they kind of gave a view of what is expected, to actually be competitive, to be accurate. And for instance, if you're looking at excitations of which are predominantly on single nature, so just one electron, not doubles and more, you could say the CC3 is quite accurate, and you're going to have, let's say, a mean absolute error which is less than 0.03 V. So this is the kind of accuracy we would like to actually have. Okay, so excited states are demanding. Of course, they are. You can think of them as open system, open shell system. So you have stronger electronic correlation than maybe many ground state problems. You might have, many phenomena. So and need to describe, going between different, potential energy surfaces. And structural relaxation is, of course, quite hard, especially if you're going away from a minimum, and something like DFT would fail in proximity of conical intersection as this one. So in some sense, also a very nice niche for correlated methods, because there are overall not many approaches which are available for the sake of relaxing the structure in the excited stage. So now somebody asked, some information about Quantum Monte Carlo. So I will just very, very quickly go through the simplest flavor of real space Quantum Monte Carlo, which is variational Monte Carlo. Okay, so variational Monte Carlo, essentially we're just using Monte Carlo techniques to compute expectation values, to compute integrals. Okay, so the energy, that's something we might want to know. That's the expectation value of the Hamiltonian, and if you work in real space, you would express the numerator and denominator as integrals. Therefore, the numerator you can rewrite, as the Hamiltonian acting on the wave function, and if you divide and multiply by the wave function, you will have the wave function square here. You bring the denominator, inside the box, and the object, which is in blue, is can be in 10 raised to 1, is positive, and can be interpreted as a probability density. Okay, so we can rewrite that for this integral as the local energy, that's the Hamiltonian acting on the wave function, divided by the wave function that depends on all electronic coordinates, and P of R. Okay, and now what you can do is you can try to sample a bunch of points in 3n dimension, where n is a number of electrons. And along, you use, for instance, Metropolis algorithm, like in classical Monte Carlo, and you compute, the local energy along your random walk. And so you estimate your energy as an average. Okay, so this is a trick to compute integrals in many dimensions. And of course, the results will depend on the quality of the wave function. And usually what we do is we go beyond variational Monte Carlo using so-called projection Monte Carlo methods to actually generate a better approximation, which will, however, depend still, for fermions, will depend from the wave function via the fixed mode approximation, okay, which was mentioned before. Now, at the moment, we are in the last, let's say, maybe decade, we have moved, to a situation where we are really ready to explore, much more as regards the performance of these methods, and also to explore excited state. Indeed, if you look at older literature, you will find a lot of total energy calculation on ground states, and often the geometries are borrowed from DFT, for instance, and also the wave function can be a single determinant times some correlative factor where the determinant is a DFT determinant. Okay, so overall has been proven a bit difficult to reach a point where it was efficient to compute energy derivative, because if you're doing things in a more straightforward manner, you're going to increase the cost by a factor of n. Okay, so order n4 for the energy, order n to the 5th for a derivative. Now has been some progress in the last decades, and we can now compute efficient derivatives analytically also for multi-determinant expansion, which means that real space QNC can perform structure and variation optimization of whatever problem you're interested in the ground state and the excited state. And I should mention that we do it analytically, but for instance, in TurboVB, in the code used by Michele, they are using algorithmic differentiation, okay, to actually reach an efficient computation of the derivative. Now, just to see why it's difficult for us, for instance, to compute interatomic forces, let's recall that, so the force is the derivative, of the energy, and we are sampling the energy, we are computing the energy by sampling the local energy. Now, if you do the math, you're going to have what you will need to sample along your random walk will be the derivative of the local energy, and this term in green, which are the fluctuation of the local energy with respect to the average energy multiplied by the derivative of the wave function. Now, if you work out all the terms, you're going to see, that you get, the Hellman-Feynman term, so derivative of the Hamiltonian. This is the so-called Poulet term, so the dependence which is present if your wave function depends explicitly on the nuclear coordinate. And then you're going to have an additional term which averages to 0, so has a 0 expectation value, but which we keep to lower the fluctuation in the computation of the energy, okay? So actually, in the limit of the wave function becoming better and better, you can actually show that keeping this term will actually give you 0 fluctuation. So you're going to need to take one step of Monte Carlo, or as the wave function becomes better and better, fewer steps of Monte Carlo to actually reach your answer, okay? However, the term needs the computation of the Hamiltonian acting on the derivative, and that's what is more costly. So in addition to get the derivative, you also get H acting on the derivative. So as I said, is it possible to actually do so efficiently for many parameters and many determinants, okay? So these are some results for a system increasing from butadiene, C4H6, to C60H62. We are not using so these are linear molecules, but we are not using the linearity of the molecule to actually study the scaling. And what we are showing is how much it costs to actually compute the energy and the derivative and the Hamiltonian acting on the derivative with respect to the cost of computing an energy alone as we increase the system size. Here, I'm showing it for wave function optimization. So we are having a simple wave function, but we are increasing the system, so the wave function gains more and more parameters, but the cost is actually limited to something less than 4. What I'm showing here instead is the same cost, computing interatomic forces plus energy with respect to computing the energy alone. We are increasing the system from butadiene to the larger one, and in the x-axis, we are having the number of determinants, so the complexity of your wave function. Okay, and what you can see that the cost will actually be always less than about 3.5. Okay, also as I increase the number of determinants or I increase, the actual system size. So this, combined with the availability of optimization tools, renders Quantum Monte Carlo finally an internally consistent method. So we can actually try to optimize our wave function and to optimize our geometry. Okay, so without relying on external, let's say, approaches. So, of course, the wave function remains key in these calculations, and what we're going to use here, what is often used, is the so-called just translator. So you're taking a summation over determinants, okay, can be 1, maybe more you need, and then you correlate with a Jastrow factor, which depends explicitly from the electron-electron distances. And there are many open questions, how do you choose the determinantal component, how compact? Often people only use one determinant, for ground state calculations. And we need to keep in mind that we want to actually reach a competitive accuracy, especially for excited state. As I said, there has been a lot of benchmarking we must compare to, okay? So now, as regards the wave function, in particular the determinantal component, if you're doing excited state calculation, people typically use a complete lattice space, which was also mentioned by Ali. So what you would do, you say, here is a cyanide dye, a small system. You say, I choose some small space of orbitals, and I correlate all the electrons in this orbital space. So here I would take the 2p atomic orbital and build 3 molecular orbital, and I end up with a CAS, so all excitation of 4 electrons in 3 orbitals. Okay, so this is the smaller system. If I go from CN3 to CN11, so I go to 11 heavy atoms, what I will have that the number of electrons grows to 12 electrons in 11 orbitals, okay? And so the number of determinants will go from 5 to something like 100,000. And note that we are only correlating the pi electrons, so the pi orbitals in the minimal number of pi electrons. And moreover, what you're going to do in Quantum Monte Carlo, you're going to start to truncate your expansion, okay? And so that's a bit arbitrary, and it's clearly not a sustainable way to go to larger system. So what we've been adopting in the last few years are actually trying to generate the determinantal expansion in an automatic manner. It's a bit like in Fusii QNC presented by Ali, but here we are doing it deterministically, and it's called selected CI. So the idea is that you start from some, let's say, few determinants, and then you expand your expansion, by connecting via single and double, via the Hamiltonian to a larger space. But you include the determinants which actually have a larger second-order perturbative contribution, okay, to the energy. And what the expert in this field would do, they would say, well, then I compute the variational energy, I have my total perturbation to second order contribution, which should go to 0 as I end up in the Fusii limit. And so you can extrapolate, you can increase your expansion and extrapolate to actually 0 PT2 correction, okay? We, of course, don't want to get here, and the question is, are these, can we get by with fewer determinants, than the original CAS expansion by using such an approach, okay? And how compact can we be? Okay, so here I will show a rather, let's say, honest slide on how we actually perform, okay? So this is a cyanide dye, so it's a pi to pi star excitation, is a cation. The 2 states have different symmetry, so in principle it should be easy. And what I'm showing here are only Quantum Monte Carlo results. So variational is full dots and empty is diffusion Monte Carlo. So here on the x-axis, we are having a different type of wave functions, okay? So we can start from the simplest. You say, well, in the ground state, I use a single determinant, and therefore I'm going to do a homo-lumo for the excited stage. But then, we optimize all parameters since we can do so. But, still the excitation will be at 5.2 and the exact one is 4.9. The scale is again 0.5 eV. So I'm very much off with respect to the best available benchmarks, So this is an extrapolated full CI and that's a CC3. Then you can say, well, I add single excitations, but actually my variational results worsen and my diffusion Monte Carlo improves, but very little. I can go to a CAS over the pi orbital, that's a minimal CAS, so sure, I'm always improving. I can put more pi, I can put the sigma, but let's say the conversion is quite slow. Okay. Now, what I'm showing, what are our best results is the use of this selected CI, so this automatic procedure of giving us good determinant. Here we range between 1,000 and 18,000 determinant, and what we're having that we are within chemical accuracy of the best result, and moreover, variation and diffusion Monte Carlo are on top of each other. We can do so for other small molecules. For instance, this is formaldehyde, thioformaldehyde. Now the scale is much smaller, 0.06 eV. So that would be, essentially beyond chemical accuracy. And again, here I'm showing in X the number of determinants. These are selected, done in an automatic manner. And I'm showing variation and diffusion Monte Carlo, which are always very close to each other, and they are actually converging to the best available estimates, okay? And overall, let's say you could conclude that if your wave function is good enough, already with few thousand determinants, you can get what you want at the level of variation of Monte Carlo without needing actually diffusion Monte Carlo. Now, how do we compute the energy, the excitation energy? We are actually computing the excitation by computing different energy states, okay? So what we do, we need to have some balanced expansion for the multiple states. And so what we do, we generate expansions of similar quality. So we either target the same variance at the CI level or the same correction, PT2 correction, viewing it as the distance from the best, from the full CI result, okay? Then we fully optimize the wave function, and we have shown also for more system, we can get chemically accurate excitation with less, less than 0.04 eV with relatively few determinants. And we can do so already in variation of Monte Carlo. And often we just use diffusion Monte Carlo as a validation that, we have an accurate actually result, so if the two are actually close. Now, okay, so we've done also, other systems, and we are always in quite good agreement with the couple cluster, but then we would like to actually go to system where other techniques, such as couple clusters, start to struggle. In particular, we would like to go to larger systems. So here what I'm showing is how we actually perform as we increase the sign-in die from the smallest, let's say, model to something with, I think, I'm not sure, 19 heavy atoms, okay? So we're always generating a CPC wave function, and what we have here, we're having DMCs taken as a 0. Couple cluster up to triple approximate is the red. VNC is always very close to diffusion Monte Carlo. The scale here is 0.05 eV, so chemical accuracy, and extrapolated full CI you can only do for the two smallest model. So we are chemically accurate for all applicable size, but we can also go to systems which, at least we found hard to deal because of memory limitations, meaning beyond 15 heavy atom, we could actually not compute the couple cluster result. In principle, we could go beyond. What is also interesting is that, and that's quite typical, we find that the smaller systems are harder than the larger ones, in the sense that to actually converge excitations, we need more determinant for localized excitation than when we actually go to a larger system. So we go, for example, from 10,000 to 5,000, going from CN3 to CN19. It was really a decreasing trend. So always remaining in the, with systems which are difficult, not just for density functional theory, but also for other techniques. Actually, I should add that the sign-in dies are very, very hard for DFT, even though they are relatively, especially the larger one, they're not so terribly multi-determinant. But, double excitation is also, generally problematic. And that is also problematic for couple cluster, meaning that to really get a good description of them, you got to need to go to quadruple excitation. So you should do CCSD-TQ or CC4, okay, which is quite expensive. So here I'm showing a vertical excitation. Now this is tetrazine. The scale is 2 eV, so there is a large spread. And these are couple cluster up to triple. Okay, so they're really very much off compared to multi-reference PT2 and our QNC calculation done with this automatically generated wave function. Okay, we go from 400 determinant to 10,000, and we're always there. Okay, but to convince, let's say, others that we're actually accurate, we need to actually look at also some smaller system. I mean, this is small enough, but even smaller. Okay. So to assess the performance, we can start from something like nitroxyl and compute the QNC excitation energy. You can see the variational and diffusion are very close to each other. Couple cluster up to triple is off by 1 eV, and the extrapolated full CI is on top of Quantum Monte Carlo. We can do glyoxal, so somewhat larger. Again, VNC and DMC are quite close. Couple cluster is off by 1 EV, and extrapolation is, okay, the error bars start to be large, but it's quite close. We are quite competitive, we are doing quite well, okay? Then you can take something somewhat larger. Now here there are 2 excitations. I'm only showing the VNC results. The VNC are not that dissimilar, but there are 2 excitations. And if you are stopping a triple, even though one of the excitation is actually of single character, you're having that the not only the actual excitation is off by almost 1 EV, but also the position of the states. So we're having they differ by 1 EV roughly, and couple cluster gets them inverted. More if you're doing extrapolated full CI, that's extremely challenging. The system is, for those approaches, quite large. But we are getting, we are getting a difference on the end excitations, which is more easy to compute, which is quite close to actually be obtained. And so we trust that Quantum Monte Carlo can be used as a good reference, for single excitation, double excitation, also, going to larger system. Michele, how am I doing?
I think it's time to wrap up, if you can.
How much? 1 minute.
Yeah, a couple of minutes. Yeah.
With questions.
Plus questions. Yeah, you should go as fast as possible to the conclusions, please. Yeah.
Very good. Okay, so I will. Okay, so now, as I said, we compute, the excitation by, looking at different states, and we're actually using energy minimization. Okay, energy minimization. Of course, it's very easy if the state had different symmetry. If they had the same symmetry, we are going to use a state-specific approach, imposing orthogonality, which is something which is also done, by Ali in the context of full CI QNC. Okay, so here I'm going to skip. And the only thing I will say is that we can relax the geometry. I promised that at the beginning. Okay, so we can also do so for the excited stage by building, let's say, a lot of consistent wave function for different geometries and different states, okay, using our smart expansion. And here what I'm showing is how the mean absolute deviation for 3 small systems. So you excite the system relaxes, okay? So it elongates, it buckles, and we are doing the mean average deviation on the bond length, okay? So as reference, we are taking CASPT2, which is available for all of them. So CC2, ADC2 are sometimes used in the literature. CC3, we could do it for the smaller system, is in green. And Quantum Monte Carlo is always quite accurate. I mean, this is variation of Monte Carlo, and the error is less than 0.01 angstrom, which I would say is pretty good, okay? At the moment, we are looking, whether we can do any photochemistry. Of course, this is a ridiculously small MD, is a very small MD, but we're actually relaxing, exciting, generating all these wave function as it goes, optimizing everything. And here we end up in a non-reactive path of the molecule, okay? We're investigating how to do so because noise is problematic and is actually quite crucial to keep the potential energy surface and the forces, to converge the forces, very well. So last, and then I wrap up, we did all of these using the CHAMP code. So that's a code that we are developing with various collaborators. And we are employing now the TREX. So our CHAMP code talks to Quantum package, which is the code generating the selected CI expansions, quite automatically. We are including also the high-performance QNCKL library to speed up the calculations. And we're having very efficient algorithm for computing observables, optimizing the structure and the wave function, and recently also for solids. And of course, as I showed you, we can treat excited state. Okay, so the code is publicly available on GitHub. So in summary, I showed you, yes, Michele, I wrap up. In summary, I show you that we have a robust protocol for modeling ground excited state. We can compute energy derivative. We can optimize the geometries and wave function. We are using selected CI to give us some automatic generation of compact wave function. We need to describe states in a balanced manner, but we can get accurate excitation and geometries, and handle different difficult systems such as doubles or larger. And so the code is CHAMP, and these are the collaborators. So the student did a lot of the work, Monica Dash, Alice Kuzzocrea, or the earlier work. Ravindra and Edgar worked a lot on the code to make it faster, and Stuart on the specific optimization. And these are senior collaborators: Saverio Moroni for Quantum Monte Carlo e SISA, Anthony Semama for Select SCI, and Wim Briers, a local collaborator. And I thank you for your attention.
Thank you, Claudia. So we have already questions in the Q&A prompt. Actually, let's start from the second one by Vitaly Gorelov. Vitaly thanks you for the talk as well. So great talk from Vitaly.
Yeah.
And then the question is if it's feasible to add the backflow correction to your wave function, and if you think this will improve the excitation energies.
Well, we don't have backflow in the code, so we have been thinking about it, but we don't have them inside. In all honesty, I doubt, but okay, I cannot say for sure I doubt, because I really think it's a question of static correlation more, and so, you know, maybe it will further compactify our expansion, but what I'm afraid is that we still will need to go to, you know, for excitation, for the excited state in particular, to go beyond, let's say, the simple, you know, homolumo or a simple wave function, okay? So it might help, but maybe not as much as one hopes.
Okay. And then it's a question about more technical, about methodology, and in particular, the difference between analytical derivatives of determinants and versus computing determinants using automatic differentiation.
Well, okay, so that's interesting. Well, okay, so it's very, so what in CHAMP we have really analytical derivatives of everything, okay? So, and what is the difference? The difference is we took some time to think how to actually rewrite the local quantities which enter in our expectation values, okay? And is a question of writing as traces and manipulating these expressions, okay? So we really have an understanding of what goes into the formula. Now, if you look at the original paper by Sorella, where he used algorithmic differentiation, you can see that he's feeding the system in a certain order as regards matrices, okay? So, and that's actually quite easy. Well, quite easy. That's quite that's quite okay for a single determinant, but for a multi-determinant, well, I'm very happy to understand how to actually do it personally. But I cannot comment. I don't have algorithmic differentiation inside my code, but everything is analytically done. So that's all I can say.
Okay, thank you. So then the last question before moving to the next talk. Always time flies too fast. About again more the HPC side of the problem. Indeed, the title of the webinar includes HPC, and it's a legitimate question and very interesting. So if this code runs on multi GPU nodes.
Okay, so now okay, so all the calculations I showed you were done on standard core processors, so no GPUs, okay? So now what we had done is we had, indeed our problem was we don't want to rewrite all codes, okay? So to run on these pre or EXascale machines. So what we had done, we actually focus our effort, actually not my effort, the effort of the computer scientist, to actually turn Quantum CKL, which is the library we are using for high performance purposes, to run on GPUs. So now we have just recently got also the GPU version of QNCKL running into CHAMP, but we have only done, let's say, toy tests, okay? So if you want a GPU version, I think you have to give us a couple of more months for our hour, but let's say other codes in the in TREX are further. For example, like Turbo VB is already running, you know, I think for some time on GPUs, and also others will instead, you know, exploit the Q and CKL to do so and avoid rewriting, you know, our own code.
Okay,
Good.
thanks, Claudia. I think it's time for closing your session. Very interesting
Okay.
talk, and thank you again for the clarity and also the pedagogical side. So you brought us from the basic of variation Monte Carlo to the to the latest developments. Thank you.
Thank you.
And it's time to move forward, and the next speaker is the next and the last speaker of this webinar is Lorenzo Monacelli. He's a researcher at La Sapienza, Rome, and they will talk about high pressure physics, in particular high pressure hydrogen, and the key role of quantum electrons and ion fluctuations to determine the hydrogen phase diagram.
So thank you very much, Michele, and let me thank once again the organizer for giving me the opportunity to be here to tell you something about my research. Today I want to tell you a bit of a story of high pressure hydrogen and how in this, which is the simplest element in our universe, actually we really need to account for electronic correlation and also to solve the quantum mechanical problem also for ions, which we usually treat as classical particles that stay there fixed or just move using classical Newton's equation, while in this case, since hydrogen nuclei are really the lightest nuclei of all, we really need to take into account the fact that they are quantum particles, quite heavier than electrons, but still it's important to account for the quantum fluctuations. And so why hydrogen at high pressure? And this is a very interesting problem and a very long-standing problem, because very long time ago, almost a century ago, it was predicted that under sufficient pressure, the hydrogen molecule should dissociate into an atomic phase where atoms form a metallic structure. And this structure was later predicted by Ashcroft in the 60s to be a room temperature superconductor, just using standard BCS theory of superconductivity. And while this remained somehow just a theoretical idea for a long time, actually in 2015 was announced the synthesization of a very high temperature superconductor in hydrides, which are based on hydrogen superconductivity in H3s, and actually was measured this material to be superconductor at 200 Kelvin. And a few years later, another hydride beat the record for the highest superconducting critical temperature, which is lanthanum H10, which was discovered to be a superconductor at 250 Kelvin, which is very close to room temperature. So we are actually getting there with the temperature, indeed, at extremely high pressure. And the reason why I mentioned these two compounds, and especially the lanthanum H10, is that if you look at the structure of lanthanum H10, this is actually, you see that the lattice of hydrogen atoms here is a dissociated lattice, so we don't have H2 molecules in the lattice, and they form a fully connected lattice where lanthanum ions actually acts as space fillers in which they do some kind of chemical precompression. And so the superconductive mechanism of lanthanum H10 is expected to be very similar to the one of high pressure hydrogen. And so probably high pressure hydrogen will be superconducting even a higher temperature, but unfortunately even a higher pressure. And so the reason why we still haven't been able, at least, so there is a claim that to synthesize I've been able to synthesize atomic hydrogen, but it's highly debated. There is still no agreement, at least let's say this, that we have synthesized atomic metallic hydrogen, and one of the reasons is that it is required an extremely high pressure, because a lot of different phases and all these other phases that you see in this sketch of a phase diagram are all molecular phases, and they are not expected to host high temperature superconductivity. And And in particular, one route to atomization of hydrogen is the low temperature route where hydrogen is in phase 3, where there have been a lot of reports of possible phase transition in hydrogen, which are contradictory between each other. And so the situation experimentally is really complex. And the reason why it is so complex is because it's very difficult to do experiments, not only because of the very high pressure, but because of the fact that we don't have access to some of the most powerful probes that usually experiment use to disentangle and understand what's going on in their samples. For example, neutron scattering experiments are not feasible at such high pressure because we don't have yet means to focus the neutron beams to sizes of the sample. And so we cannot isolate the signal arising from the hydrogen compressed inside the diamond atom itself from the one of the gasket and the environment. And for X-ray scattering, which is in principle feasible at a high pressure, it's not very reliable on hydrogen because X-ray usually interacts with core electrons, and hydrogen has 1 electron per nuclei. So the cross section of X-ray is really small. So hydrogen is almost invisible to X-rays. And so the only probes we have to understand what's going on in a sample are all indirect probes, like electrical resistivity, optical spectroscopy, so essentially what color is the sample and how does it look on the camera, and vibrational spectroscopy. And so while these three tools are quite powerful to understand if there is a phase transition, in the sense that if our sample is transforming into something else, we expect discontinuities in these observables, at least in some of these observables, they don't tell us anything directly related to what is the phase of the system we are studying. And so for these reasons, we must rely on simulation to understand the situation. But however, also simulations are extremely complex. And thanks to the progress made from crystal structure search, we now have a lot of candidates for being the ground state of high pressure hydrogen and be the actual molecular phases. However, those are a lot, and the energy difference between them often is below 1 millielectron volt per atom, which is below chemical accuracy. And this means that density functional theory is not able to disentangle between these phases which one is the real ground state, and we must rely on more advanced technique like the diffusion Monte Carlo. And the other problem is that the one that was anticipating before is the fact that protons are extremely light, so we cannot treat them as classical particles, and 0-point energy of the protons in our system needs to be taken into account and plays a major role. And so we must do quantum simulation also for the nuclear part of the system. And so here, just to give you an idea on this, these are few of the phases we take into account in our study. There are also many others, but here I depict for some of these different symmetries the average structure with the bigger spheres, and these small spheres are not the electrons. So those are actually samples of the quantum distribution of the nuclei. And so as you can see, and these are 0 Kelvin, so this is purely 0-point motion. And so as you can see, the 0-point motion of this nuclei is really sizable and is a non-negligible part of the interatomic distance, both inside the same molecule and across different molecules. And so not only 0-point energy is important, but also beyond harmonic approximation, because as you can see, when the atoms and the molecule will stretch that much as the edge of this probability distribution, we will trigger a lot of anharmonicity. We can trigger bond breaking and so on and so forth, which is important in the thermodynamic of these, to study thermodynamics of these phases. And so what is the theoretical framework that we use to study this system? So we must simulate both electrons and nuclei from first principles, and we rely on the adiabatic approximation. So electrons are always in their ground state, no matter where the nuclei are. And so the electronic problem is solved using Quantum Monte Carlo, as I was telling you, as implemented the Turbo RVB code. And actually, to be able to do an actual simulation, we evaluate, we do a mixture between quantum Monte Carlo and density functional theory, as we'll explain, so that we evaluate energy in a delta sampling way. So what does it mean? It means that we actually do the full simulation using density functional theory. Then for each pressure and each phase, we take the most likely configuration for the nuclei taken from the nuclear wave function. So we take the maximum of the probability distribution of the nuclear wave function for each nuclei, and we do a one-shot diffusion Monte Carlo calculation on this configuration to rescale the energy of each phase on a per phase per density base. And so you can see these different structure, how they are corrected, or how diffusion Monte Carlo corrects the energetic with respect to the density of the different phases. And so the higher on this plot means the bigger correction, in this case negative, so tends to favor more diffusion Monte Carlo with respect to the DFT results. And so we can immediately recognize, apart from one phase, we can immediately recognize two different trends. One trend is these two lines here, which are two very similar molecular phases, where DFT seems to require a larger correction, and the other one is from a strongly metallic phase, one of which is atomic, purely atomic hydrogen. So this message is that DFT does much better metallic phases than molecular phase, but that's it's some kind of known, but it's interesting to see naturally in practice. This has a consequence indeed on the phase diagram, which means that if you do the phase diagram using density functional theory, you will tend to have the transition to the metallic phase much earlier. And this is why people thought in the past that atomic hydrogen was easier to be reached, because DFT results were metallizing hydrogen earlier, because they were favoring the metallic phase with respect to the actual molecular phases. And there is one exception, as I will tell you, which is this green line. And this green line is a very peculiar phase we discovered, in which you have mixture between graphene-like sheets of hydrogen and molecular layers. So it's a layered phase. And so at low pressure, it behaves like a molecular phase, while at high pressure, it behaves like an atomic phase. And even more instantly, as we increase the density, so we increase also the pressure, the difference between all these phases shrinks down. And so this means that the relative energy of density functional theory will be better. However, if you look at the difference here between all these energy, it's actually way above the 1 millielectron-volt per atom that I was telling you is the required accuracy that we really need to study this system. And so this is our theoretical framework to describe electrons. What about nuclei? So as I told you, we need also to solve the nuclear problem using quantum mechanics. And we use a technique which resembles a bit some kind of variation on Monte Carlo. It's a bit different. It's called the stochastic self-consistent harmonic approximation. But it works more or less like a variation on Monte Carlo for the nuclei. And so what we do is that we describe the nuclei, the nuclear density matrix, as a trial density matrix. At t equals 0, this is just the trial wave function of the nuclei, but this allows us to do also finite temperature. And this density matrix is described as a Gaussian. Now, this is very good usually for nuclei, because while electrons tend to be very delocalized, especially in metallic phase, nuclei, even if they fluctuate a lot, are usually localized around the site position. So Gaussian is the maximum entropy, if you want, wave function to describe something which has a fixed average position and fluctuation. And we also have correlation between nuclei, which is described by this matrix, which couple all nuclei with each other. We have a two-body correlation, which is enough usually in this kind of system. And so we take this wave function, or density matrix if you want, and then we optimize the parameters, which are the average position of the nuclei in our system and the quantum fluctuation described by this matrix, covariance matrix here. And these are optimized in order to minimize the free energy. So that's why I was telling you it resembles a lot the way of variation of Monte Carlo works, but for nuclei this time. And so here to give you a simple example in a one-dimensional system, so we take a strongly anharmonic one-dimensional system, we can compare here the harmonic wave function, which is we find the minimum of this potential, then we expand the potential up to second order, we get a harmonic potential, and then we solve the harmonic potential, which the ground state of harmonic potential is a Gaussian, which is this red line here. And if we take this Gaussian and now we optimize the parameter from this Gaussian to minimize the energy, we get instead this green result, which is the self-consistent harmonic approximation result. And this is how it compares with the exact solution, which indeed is not Gaussian, it's more complex. So as you can see, the wave function is not perfect, but who cares in this case? Because what we really care is the energy and the observables, which is, for example, the average position of the nuclei. And both the energy and the average position are actually described very well because they are second order, thanks to the fact that we are using a variational approach. So now let's return back to hydrogen. And as I was telling, we have so there have been a lot of contradicting results, especially in the low temperature, high pressure region. And so when we start from relatively low pressure, I mean 300 gigapascal, it can be assumed as a low pressure, and we compress the system, several different observables were spotted in the experiment. So one experiment by the group of Mikhail Eremets showed that this system became a conductor at 360 gigapascal with a sudden transition. So they saw an onset of conductivity at 360 gigapascal. And then a different experiment, which was published just a few months later by Paul Aubert, showed that was observing the sample looking at infrared light. And what they observe is that the sample is transparent and remains transparent above 360 gigapascal. So it seems to be in contradiction with this other experiment because metal should reflect light, not being transparent to them, up to another pressure, much higher, 420, where the sample suddenly became opaque, so either reflecting or absorbing all the light. And so they claim this was another transition. And while if you look to the optical spectrum, so to visible light, nothing very interesting is happening, except the sample formed transparent, became reddish around 300 gigapascal, and then black. And between 360 gigapascal and 420 gigapascal, it's black. So it seems from experiment, we have a black, transparent in the infrared, but conductive metal, which seems to be a contradiction. And so to shed light, there is some issue in the experiment, or how to interpret these different results, we perform fully ab initio simulation with the techniques I told you. And this is the results of our phase diagram. And so I plot here the enthalpy on the y-axis as a function of pressure. So the ground state, I report only the phase that wins here, the race for the ground state. And so the ground state is the one that at fixed pressure has the lowest enthalpy. So the lowest curve in this plot here is the ground state. And so as you can see, at low pressure, we recover phase 3, which was discovered by Grispikar et al. For the first time. And indeed, this remained ground state for a wide range of pressure up to 410 gigapascal, where a new phase, a different phase, originally proposed as an alternative to phase 3, but which actually is a different phase of hydrogen, is stabilized and became the ground state. And then we have this phase that is stable for a wide range of pressure, more than 150 gigapascal. And then this phase transits finally into the atomic phase, which is predicted to be the room temperature superconductor at much higher pressure than thought before, which is 577 gigapascal. So as you can see, unfortunately, we are still very far from realizing metallic hydrogen. And one thing to notice is that if we simulate the ions using the harmonic technique, so we just take the harmonic 0-point energy, we end up with something which is completely wrong as in the phase diagram. So we end up with phase 3 that directly transit into the atomic phase, or the it depends a bit on the error, because this transition happens very close to where phase 6 is. So depending on how you do your diffusion Monte Carlo, it can be that phase 6 is stable in a very narrow region here, but it's something which is completely different from the real phase diagram. So that's how to say that quantum effects and quantum anharmonic effects on nuclei really are important. And indeed, if you do this with standard DFT, you end up with something which is also completely different from this one. And so now that's the phase diagram, but what about the experimental results? So we need to compare now with the experimental results. And so to do so, we simulated the electrical properties of phase 3 under pressure. And so we simulated the band gap, and particularly we accounted for electron-phonon interaction and also the discontinuity in the exchange correlation potential. So we used a meta-GGA here, which is the modified Baylor-Johnson, to compute the band gap. The reason why we didn't go directly with diffusion Monte Carlo is that to converge the electron-phonon interaction and the in this system, we need to go to system that contains several hundreds, if not thousands, of atoms. And as you can see here, if we follow the band gap closure as a function of pressure, we end up very close to the onset of the experiments of conductivity. And so you can explain actually the onset of conductivity observed in the experiment by the group of Eremets is actually just the closure of the band gap, is not a phase transition. While if we now simulate the absorption factor in the infrared and we compare phase 3 here, these are our simulation with the results from infrared spectroscopy. So this is the absorption threshold, so the highest frequency that that the sample is transparent. We observe that there is a very good agreement with the experiment up to a certain point, where experiments suddenly became we have a sudden transition in the experiment, but this transition here match very nicely with the transition point at which we predict phase 6 to become stable. So that's a way in which the transition observed by the group of Polo Bear is actually a real phase transition. And more interestingly, we now have also explained one apparent contradiction, because we have a region below this phase transition here, but above the pressure at which phase 3 became stable, in which hydrogen behaves like a transparent metal in the infrared. And while this may seem a bit absurd, because metals should reflect all wavelength below the plasma frequency, you can actually see me right now and see this presentation right now through a transparent metal, because another example of transparent metal is indium tin oxide, which is employed to make LED screen. And the reason why both indium tin oxide and high pressure hydrogen are transparent metals is the fact that they have a very small plasma frequency. In the case of hydrogen, is because of the presence of interband transitions that push down a lot the plasma frequency. And the fact that the density of states at the Fermi level is also very low. And but to actually confirm that the phase transition to phase 6 could actually be the one that explained, we also repeated the transmitted calculation on phase 6. And what we observe is that indeed no transmitted light occurs on phase 6 across the phase transition. So actually, we expect a drop in the transmitted light in the infrared between the transition to phase 3 to phase 6. So moreover, we were able also to do a prediction, because for us, changing between hydrogen and deuterium is just changing a number in the mass of the system in the simulation. So we recomputed the full phase diagram also in the case of deuterium, predicting an isotope effect in the phase transition of about 30 gigapascal. And a few months later, our work was published in Archive. Actually, Polo Bear presented a new work in which they show that they had done the experiment on deuterium and show a very similar isotope shift with respect to the one we predicted. And so we not only explained what was going on before, but we were also able to do a prediction that was later confirmed by the experiment. And so last but not least, we also were able to simulate how the sample should look like under visible light, which is the other observable that we have. And as you can see, we can explain the reason why the phase 6 transition we were not able to see from visible light only. And the reason is that under visible light, so here you see the spectrum of visible light, the reflectivity of phase 3 and phase 6 is very similar. So it's almost impossible to not notice this with the actual experimental resolution. And here is how it should look like the sample, so blackish, poorly reflective sample of the system. And then as we increase the pressure, the reflectivity gradually increases because the conductive property of phase 6 increase until we transit into the the atomic phase, in which it's more shining, but it's a dirty shiny metal because of the fact that interestingly, electron phonon kills a bit the reflectivity of the metallic phase, the atomic phase, while it promotes strangely the reflectivity of the molecular phases. So electron phonon seems to act in a different way in metal, in the pure atomic structure and in the molecular metallic structure. So thank you very much for your attention. And my conclusion is that behind our result that we get on hydrogen is that state-of-art theoretical simulation can be predictive if we are able to simultaneously account for high-level electronic methods like diffusion Monte Carlo and also the quantum nature of nuclei in this case that are very important. So thank you very much, and I open to questions.
Thank you, Lorenzo. So indeed, the session is open to questions. It's the last talk, so everybody is quite tired after a full day of talks and discussions. So, I mean, I have one maybe. So you showed several agreements with experimental probes in different sectors of also the spectrum. How this work compares with other results? I'm thinking, for instance, about the direct the band gap computed, for instance, by other groups, by other QMC groups.
So yes. So for example,
compare what we got, because I'm co-author of this work.
Yeah.
And what the other groups got by using quantum Monte Carlo techniques as well.
So yeah.
How this compares with the previous works.
So there are several. So there have been a lot of works indeed trying to measure the both indirect and direct gaps of high pressure hydrogen and with different techniques. So actually, for what regards this phase, there was another work from Gorelov, for example, who measured who computed using diffusion using Monte Carlo techniques the band gaps, and for example, the case of phase 3 band gap, we have a very good agreement with them. All our dots are almost overlapped with them, so the closure of the band gap it's almost the same here, and the differences between our calculations, I would say, are indeed they used a more accurate technique for the band gap as they use Monte Carlo, and why we rely on this meta GGA. But on the other side, we somehow went to a bit more bigger cells to simulate the effect of electron phonon, which we found very important. So maybe these two things somehow counterbalance exactly in the case of phase 3. I think we have some difference in the case of phase 6 instead. So the point for us was that what I found is that what is very important in this kind of phase is it's important to have a good accuracy on the technique that you use to measure the band gap, but also in the case of electron phonon, in the case of this kind of electron phonons, where here, for example, the electron phonons acts for several electrons, so it's almost 2 electron volts of renormalization of the band gap due to electron phonon in the case of hydrogen, which to my knowledge is the highest ever measured, reported. And in this case, it's really crucial to have to sample very well the Q points of the phonons to have a good estimation of the electron phonon renormalization of the band gap, which can affect the results of several hundreds of milli-electron volt, which is relevant in the case we want to be compared with the experiment. So the message in this very strong, the electron strongly, where electron phonon is very strong, like I mean, case of a potential superconductor of several hundreds of Kelvin, indeed BCS, it is the case. Then it's very important to study it on big supercell, if it's a supercell technique, or big Q mesh for the phonons.
Okay, thanks, Lorenzo. I think it was important to specify these aspects and also highlight the work previously done by other groups, because it's a very, as you know, it's hot topic.
Hot topic, yeah.
And many groups, particularly in Quantum Monte Carlo community, are working actively on that. All right, so other questions? So yes, a question from Mohamed Benaissa. Can we introduce plasmon scattering in the simulations?
So that's a difficult question. So I would say it's going to be quite tricky. So this case, as I was telling you, is a fully adiabatic approximation. So in which somehow we treat electrons and always in the ground state. So indeed, in the case of hydrogen, there were so especially if you go here, so very close to the phase transition, you see immediately that you have the indirect band gap, which is of the order of half electron volt, which is comparable with somehow the high energy of the highest energetic phonons in the system. So you may expect some kind of coupling between electrons and phonons even in the ground state. And however, since we were studying mostly ground state property, not we neglected the non-adiabaticity in this system, which I think it's still a very good approximation. In this case, we tested indeed what was the difference even in this kind of electron phonon calculation to exclude some of the most high energetic phonons. And but indeed, we should, so there is no end to the possibility to go beyond approximation. So in case you want to study just the ground state energy, at least of this system was not relevant, I would say. But I mean, indeed, if you want to do excited state properties, probably yes, it's a.
Okay, thank you, Lorenzo. So is there any other question? I haven't seen raised hands or other messages in the query. I think it's time to then close this webinar. So thanks again, Lorenzo, for your nice talk and the nice results you got. Yes, so there is the last part, which is a wrap up and what's next. And everybody is invited to contribute. I can just give you my personal impression of this webinar. So First of all, I think the speakers have shown that QMC techniques are very versatile, because we have seen successful applications in different topics, different fields, which are very different from each other, and yet being extremely well performing and getting accurate and I would say state-of-the-art results. And the second point is also the maturity of Quantum Monte Carlo, because as we have seen, those fields are very competitive. We have many methods used to solve the actual problems. So the toolbox is rich of methods we can use, and Quantum Monte Carlo shows its appeal. I would say its accuracy, so maybe it's an abused word in the Quantum Monte Carlo community, but indeed now we have ways to compare Quantum Monte Carlo against highest level method, for instance, full CI in quantum chemistry, or against experiments, as we have seen with Lorenzo Stock, where we have many experimental probes available. So the maturity is also a point to highlight. So the versatility and maturity, and then of course the HPC component, which is highlighted also in the subject of the webinar. So it's also developing to such that the codes, the QMC codes, can be first of all more user-friendly and more available at a larger community, and also more easily ported to new architectures like GPUs. We had many questions about the GPU portability of QMC codes. So this part is also very important, such that the codes are ready for the next generation of HPC machines. And that's also one of the legacy of the TREX collaboration, right? And also that's to conclude for my side, and I give the floor to anyone who'd like to intervene. There is also this attempt to combine Quantum Monte Carlo with other techniques. We have seen the combination with DFT, with Katarina to develop new functionals, the combination with machine learning techniques, combination with CPC, as shown by Claudia, so combining high-level quantum chemistry with advanced wave functions. And then also the attempt to combine this with the quantum description of nuclei in general with dynamics, thanks to the evaluation of forces. And finally, also to model the systems using spin lattice or spin Hamiltonians. So this sort of cross-fertilization is something I think to be developed in the future as one of the challenges ahead. So that's my viewpoint, and then I leave the floor maybe to maybe to Claudia and Sarah and anyone else who would like to give his contribution.
Well, Michele, you spoke very well, so I don't have much to add. No, I don't have much to add. So we mentioned here mostly applications, but let's say if this triggers the interest of some of the people, you should not hesitate us to approach us also for the use of the codes. So we tried. I very quickly flashed the general website where you can assess everything, but let's say if you have a hard time, just contact us. Okay, so QMC method so they are costly. They are often interfaced with other approaches, to get a starting wave function, and this can be a bit intimidating, but we are actually developed some tools to make all of this rather automatic, much more automatic and much easier for the users. So this is an invitation to start to use the methods yourself, okay? And then I'm sure I let Sarah add something.
Oh, this is going to be difficult because two reasons. First of all, most of the scientific points have been touched very, very well by you, Claudia, and by Michele before you. And also, while I'm a passionate observer of what happens in Quantum Monte Carlo, I am certainly not a practitioner. So what I can say is that from that point of view, today was extremely useful because you provided a very nice overview of the possibilities of these methods. And also, I think now, if I put my CECAM deputy director hat on, I think that's something that emerged very nicely is the relevance of, you know, the international collaboration network to enable not only development of new methods, but actually, you know, the implementation and deployment in codes that then are of use to a broader community. So, I mean, I can only say that I'm, you know, been super happy to participate in the webinar and learn from you. And maybe, you know, this is the opportunity to extend the tools to build on the work that has been done in TREX. I think that that would be really, really useful, you know, to make sure that all the expertise that you have grown and put in place with your efforts gets transferred to as broad a community as possible.
Well,
Okay.
yeah, we should thank Sarah indeed, you know, for
Yes.
holding this thing together. It's very useful also to reach, indeed, a quite broad audience, the audience of CECAM, indeed. Yeah. So, Michele, I'm sorry, let you finish.
Yeah, no, so I'd like to highlight, I mean, a sort of this joint collaboration, which has been very nice to put up this webinar. And I think it's sort of natural. I would like to highlight that it requires some work, but it's a natural, I would say, way of working together, because our interests, I think, perfectly overlap with the CECAM also goals, as Sarah pointed out at the beginning. All right, so if anyone else would like to say something, I don't see any comment or any raised hands in the list, so I think it's time to conclude. We are a little bit behind the schedule, but not that much for the you know, the number of talks and the exchange we had today. So I'd like to thank everybody, and it has been very interesting to listen to the speakers and to take your questions and then to convey these questions to a nice discussion. So thanks a lot, and have a nice day. And I give you the invitation to the next TREX meeting, which will be held actually in like a couple of weeks in Luxembourg, and eventually the next TREX events. All right, thank you, and bye-bye. See you.